Our galaxy isn't just drifting through space as a single isolated island of stars. It's surrounded by a swarm of much smaller companions. These tiny galaxies orbit us like cosmic moons. They are locked in a slow gravitational dance. This dance has been going on for billions of years. They don't look impressive compared to giants like the Milky Way or Andromeda, but without them, the universe as we know it would be unrecognizable. Some of them are being pulled apart as we speak. Their stars are stretched and torn. This leaves behind long, ghostly rivers of starlight across the night sky. Others may be pristine time capsules from the very dawn of the cosmos. They carry within them the secrets of how the very first galaxies formed. To study them is to peel back the layers of our own galactic history. It is to witness the brutal and beautiful processes of cosmic cannibalism, and it is to glimpse the ultimate fate of the Milky Way itself. What counts as a galaxy setting the boundaries? When we look at the night sky through a powerful telescope, we see countless collections of stars. Some are vast, majestic spirals, stretching across hundreds of thousands of light years. They blaze with the light of 100 billion suns. Others are far smaller, and so faint they appear as little more than hazy smudges against the darkness. To the human eye, they can all look similar points of light, grouped together in the deep black. But for astronomers, there is a profound and surprisingly difficult question hiding here. What actually counts as a galaxy? At first, the answer seems simple. A galaxy is a huge group of stars bound together by gravity. But when you look closer, the line becomes much harder to draw. It's the line between a true galaxy and a simple, oversized cluster of stars. And it's much more interesting. The deeper astronomers have peered into the cosmos, the more confusing this boundary has become. And the more important, a galaxy is a system, a living, evolving environment of matter, gas, and powerful invisible forces. For many scientists, one key trait separates a true galaxy from a simple star cluster. This non-negotiable trait is the presence and influence of gravity. In small, simple star clusters, the gravity comes only from the mass of the stars themselves. But in galaxies, there is a crucial extra element: dark matter. This mysterious invisible material makes up most of a galaxy's total mass. We can only detect it through its gravitational pull. It acts as a kind of invisible gravitational glue. Dark matter forms a vast spherical halo around the galaxy. This gives it the immense gravitational strength to pull in fresh gas. It shapes the orbits of its stars. It can even resist the powerful gravitational pull of nearby larger galaxies. If you could somehow strip away this unseen halo, the entire structure would quickly fall apart. For this reason, many astronomers argue that a true galaxy must show clear signs of being supported. It must be dominated by a halo of dark matter. Larger galaxies like our own Milky Way often pull on their smaller neighbors. They tug at them with powerful tidal forces. These forces can stretch and twist a smaller object until it breaks apart completely. Star clusters lack the protective shield of a dark matter halo. They are often shredded over time when caught in the orbit of a giant galaxy. Their stars are scattered across the sky, forming long, thin streams. But dwarf galaxies, even the tiniest ones, often remain intact for billions of years. Their massive, invisible dark matter halos protect them. They act as a gravitational anchor. This helps them hold together despite the immense tidal forces of their larger neighbors. This incredible endurance is one of the key reasons astronomers treat them as real galaxies. It is their ability to survive in a hostile environment. They are not just star clusters, but not every system fits neatly into this simple rule. Some of the faintest, most ghostly galaxies ever discovered seem to deliberately blur the boundary. Ultra-faint dwarf galaxies, for instance, contain only a few thousand stars. Sometimes they have even fewer than a large star cluster, yet they behave very differently. their stars are spread out over a much wider area, and they move in ways that suggest the presence of far more mass than we can see. The only viable explanation is that these tiny faint systems are dominated by dark matter. Their stars are just a tiny visible frosting on a massive invisible cake. In this way, galaxies that look small and fragile can still count as true galaxies. This is because their invisible scaffolding is so immensely strong. Another crucial trait often separates galaxies from star clusters. This is the ability to create new stars. In many galaxies, vast clouds of cold hydrogen gas collapse under their own gravity. This forms new generations of stars. It's a cycle of birth, death, and rebirth that can continue for billions of years. Star clusters, on the other hand, are usually born in a single explosive burst. After their first round of stars ignite, they quickly burn through their available gas. With no fuel left, they cannot make new stars. This difference in star formation history is a crucial distinction. It makes galaxies evolving dynamic ecosystems. Most star clusters are more like static fossils of a single ancient event. If you look at the chemical makeup of the stars within these systems, this contrast becomes even clearer. Galaxies typically show a wide variety of chemical fingerprints. This is because each new generation of stars forms from enriched gas. This gas has been enriched with heavier elements by the supernovae of older, massive stars. Star clusters, by comparison, usually show a much simpler, more uniform chemical record. All of their stars were born at the same time and from the same primordial cloud. Their chemical history was locked in at the moment of their birth. Still, even here, the edges begin to blur. Some of the largest, most massive star clusters like Omega Centauri show signs of chemical complexity. This resembles the complexity of a small galaxy. In fact, some scientists now believe that Omega Centauri might be a remnant core. It could be the dense core of a dwarf galaxy. This dwarf was stripped of its outer stars and gas long ago by the Milky Way's tides. This intriguing possibility shows just how tricky and dynamic the boundary is. Objects can change over time, moving from one category to another. A small galaxy torn apart by powerful tidal forces can leave behind what looks like a simple star cluster. A star cluster that holds on to more mass than expected might be a leftover core. It might be the surviving core of a destroyed galaxy. The way the stars move within a system tells you about the gravity holding it together. In star clusters, the motions of the stars can be explained by the visible mass alone, but in galaxies, the stars move too quickly for the visible matter to keep them bound. This is especially true for stars in the outer regions. Something else, a vast unseen mass dark matter, must be there, tipping the gravitational balance. By carefully studying these stellar motions, astronomers can decide. They can determine if a faint, distant object is truly a galaxy or just a cluster. Even with all of these carefully considered criteria, there are still passionate debates. Some astronomers argue that insisting on dark matter as a strict requirement is too restrictive. This is because in certain rare cases, galaxies can lose their dark matter. This happens through violent interactions with other galaxies. Others suggest that star formation is not the best marker. This is because even large, healthy galaxies can eventually run out of gas. Then they stop making new stars. What remains constant, though, is the idea of complexity and history. A galaxy is not just a simple group of stars that happen to be stuck together. It is a complex, long-lived system shaped by both visible and invisible matter. It is built to last and capable of evolving across the vast stretches of cosmic time. If we draw the line too narrowly, we risk overlooking important systems. These small systems may hold the deepest clues to how the very first galaxies formed. If we draw it too widely, we risk blurring the unique processes that make galaxies different. The faintest galaxies ever found push our very definition to its absolute limits. Are these ghostly, ephemeral systems truly galaxies? Or are they something in between, a new category of object that challenges our neat boxes? The answer is still unfolding. This uncertainty reflects a larger, more profound truth about the nature of science. The universe does not always fit neatly into the categories that we create. Our definitions are simply tools meant to help us understand, but the cosmos constantly and beautifully challenges them. In the case of galaxies, this challenge is particularly sharp. This is because these systems are so central to the overall structure of the universe. They are the homes of stars, of planets, and perhaps of life itself. Understanding where galaxies begin and where they end helps us to understand something important. It helps us understand how the universe itself is organized. The realm of the small dwarf galaxies explained. If the great spiral galaxies and giant ellipticals are the majestic lords of the cosmic stage, then the dwarf galaxies are their quiet, often overlooked companions. They may not dazzle the eye with sweeping star-filled arms or brilliant glowing cores, but they are everywhere. In fact, when astronomers count the total number of galaxies, the overwhelming majority are dwarfs. These are the true lightweights of the galactic family. They are small, faint, and sometimes so ethereal they are almost invisible. They hide against the vast, dark backdrop of space. Our own galaxy, the Milky Way, contains somewhere between 200 to 400 billion stars. This depends on how you count them. A typical dwarf galaxy, in stark contrast, may have only a few billion stars or even fewer. Some of the tiniest, most extreme examples, the ultra-faint dwarfs, contain just a few thousand stars. To put that in perspective, a single large star cluster inside the Milky Way can contain more. It can contain hundreds of thousands of stars. A typical dwarf galaxy might span a few thousand light-years across. This is compared to the Milky Way's 100,000 light-year diameter. Some are so compact they would fit comfortably inside a single spiral arm of a large galaxy. Others are puffed up and spread out. Their stars are scattered so thinly across a vast volume that they seem almost transparent. Despite these dramatic differences in size and appearance, one thing unites almost all of them. Dwarfs lack the grand, well-structured forms of the larger systems. They do not have the neatly wound, elegant spiral arms we see in galaxies like Andromeda. Nor do they have the smooth, glowing balls of stars seen in giant elliptical galaxies. Instead, they often appear irregular, lopsided, and messy. Their stars are unevenly distributed. Their gas clouds are ragged and torn, as if they were never quite finished being built. This irregular, chaotic look is partly the result of their inherent weakness. Because dwarf galaxies have less mass, their gravity is not as strong. That means they have a much harder time holding on to their precious reserves. These reserves are stars, gas, and dust. A close encounter with a larger galaxy can violently distort them. It can pull them out of shape, leaving behind a warped, stretched-out appearance. Many of the dwarfs that we see are satellites of bigger galaxies. Their current appearance often shows the deep, brutal scars of these ongoing interaction. Even so, dwarf galaxies are not just leftovers or cosmic scraps. They are thought to be some of the very first building blocks of the entire universe. In the early cosmos, small, dense clumps of gas and dark matter began to gather. This happened long before the giant galaxies had formed. These clumps became the first dwarf galaxies. Over billions of years, many of these small primordial systems merged together. Their stars and gas combined to form the larger galaxies we see today. In this way, the great spirals and ellipticals are the product of countless smaller systems. These systems combined over the vast expanse of cosmic time. Some of the dwarfs, however, survived this violent process intact. They continue to orbit as satellites around their bigger, more massive cousins. These survivors are incredibly valuable to science. They may carry with them precious clues about the very first galaxies. They hint at what those galaxies were like in the earliest, most formative times. Not all dwarfs look the same. Astronomers divide them into different categories based on their shape and their behavior. Some dwarfs, called dwarf spheroidals, are very diffuse and faint. They often contain very few stars spread across a large volume. They show almost no signs of gas and little to no new star formation. This makes them ghostly dim and almost fossil-like objects. Others, called dwarf irregulars, are much more active. These are clumpy, gas-rich systems where new stars are still being formed. In fact, dwarf irregulars can shine quite brightly in certain regions. They have glowing clouds of hot gas lit up by brilliant clusters of young, massive stars. There are also dwarf ellipticals. These are smoother and rounder than the irregulars, but they are much smaller than the giant elliptical galaxies seen elsewhere. Compared to the large galaxies, dwarfs tend to be poor in heavy elements. Stars create these heavy elements through nuclear fusion and in violent supernova explosions. But in the small, gravitationally weak dwarfs, many of these precious materials escape. With their weak gravity, they cannot hold on to the powerful blast of a supernova. Large galaxies can hold on to it much more easily. Over time, this means that their gas remains relatively primitive. It is more chemically similar to the gas of the early universe. Astronomers can thus use them to study conditions similar to those that existed long ago. This was before galaxies like our own Milky Way were fully developed. Despite their low star counts, dwarf galaxies seem to be completely dominated by dark matter. In fact, pound for pound, they often contain far more dark matter than the giants do. This is relative to their visible matter. This is why they can survive at all, even when they are so faint and so fragile. Studying these dark matter halos helps scientists learn about the nature of dark matter itself. Some of the smallest known dwarfs have been called dark matter laboratories. This is because of how sensitive their stellar motions are to its invisible presence. The Milky Way is surrounded by dozens of known dwarf galaxies. The most famous of these are the large and small Magellanic Clouds. They are visible to the naked eye in the southern hemisphere. These two irregular dwarfs are gas-rich and full of young stars. They are currently interacting with both each other and with the Milky Way. Their distorted shapes and active star-forming regions are clear evidence of this ongoing dance. Closer in our galaxy also hosts a population of tiny, faint, spheroidal dwarfs. Some of these were only discovered in recent years through meticulous surveys of the sky. These faint companions are so diffuse that they almost vanish into the star-filled background. Yet, they are still galaxies in their own right, held together by their own dark matter. Other large galaxies also have their own retinues of dwarfs. The Andromeda Galaxy, for example, is accompanied by more than 30 known dwarf galaxies. This forms a miniature system of its own. In fact, dwarf galaxies are so common that astronomers believe there may be far more of them. Many could be waiting to be discovered. This is especially true in regions of the sky that are harder to observe. Many of them could be hiding at the very edge of detectability. They are faint clouds of stars that require the most powerful telescopes in the world to spot. Though they are small, dwarf galaxies can still make a very big impact. When a large galaxy absorbs a dwarf, it can stir up new star formation. It can add fresh gas to the larger system, and it can alter the larger system's overall structure. Our own Milky Way shows clear signs of having consumed dwarfs in the past. This process has left behind long, ghostly trails of stars in its halo. Some of the globular clusters in our galaxy may even be the surviving remnants of ancient dwarfs. These dwarfs have been stripped down to their very cores. In this sense, the dwarfs are both the seeds of the larger galaxies, and they are the fuel that continues to shape them over time. There is also a profound mystery that is tied to the dwarf galaxies. This puzzle is known as the missing satellites problem. According to advanced computer simulations, galaxies like our own should be surrounded by hundreds of companions, maybe even thousands of small dwarf companions. Yet when astronomers look, they find far fewer. Either we are still not seeing the faintest ones, or something about the way that galaxies form is different from what our best models predict. This puzzle remains unsolved, but every new dwarf galaxy that is discovered brings us one step closer to an answer. The hidden majority of galaxies in the universe, the large galaxies, shine like brilliant lighthouses in the cosmic dark. The dwarfs are more like faint, scattered sparks everywhere but easily overlooked. Their small size and their low brightness make them nearly invisible in wide surveys of the sky. To detect them requires deep, careful and patient searches, and often even then they remain little more than faint, hazy smudges against the deep blackness. Astronomers have learned to look for these hidden galaxies in clever and ingenious ways. One of the most effective approaches is to search near the larger galaxies. This is where the dwarfs often cluster as companions. Around our own Milky Way, the large and small Magellanic Clouds are the easiest to see. But the fainter satellites are so dim they are only visible through detailed surveys. Satellites like the Draco Dwarf or the Ursa Minor Dwarf. These surveys track the motions and brightness of millions of stars. As our telescopes have improved, more and more of these faint companions have been discovered, and each new find suggests that there are many more of them still waiting to be revealed. Another powerful method is to use wide-field digital surveys that map the entire sky. These surveys do so in exquisite detail. In recent years, projects like the Sloan Digital Sky Survey have uncovered dozens of these dwarfs. They did so by picking out subtle clumps of stars moving together through space. These remarkable discoveries have shown that the universe is teeming with these small, faint galaxies, and yet astronomers are convinced that we have only found a tiny fraction of them. When scientists run their large-scale computer simulations, they begin with dark matter halos. These vast, invisible halos form from the gravitational pull of dark matter. They draw in surrounding gas and create the conditions for the first stars to form. In these models, the small halos form first. Then they merge together over billions of years to create the larger ones. This process naturally produces an enormous number of small galaxies, far outnumbering the giants. It is a bottom-up picture of cosmic growth, where the small arrive before the big. The evidence from our own local group of galaxies supports this view. The local group includes our own Milky Way and the Andromeda Galaxy. It also includes a collection of smaller galaxies, and it is completely dominated by dwarfs. Beyond the two giant spiral galaxies, nearly every other member of the group is a dwarf galaxy. Some are irregulars, still forming stars. Others are spheroidal, so faint they are barely visible even with our most modern instruments. This small corner of the universe offers a perfect snapshot of a broader universal truth. Wherever there are galaxies, the dwarfs are the most numerous. A dwarf galaxy with only a few million stars produces far less light than a spiral galaxy. A spiral galaxy has hundreds of billions of stars. By the time that dim light has traveled across millions of light years, it becomes almost undetectable. Our telescopes must compete not only with vast distances, but also with the faint glow of background stars, and with cosmic dust, and even the light pollution of the Earth itself. Many of the dwarfs simply blend into the cosmic background like shadows. Detecting them requires extremely long exposures and the most sensitive instruments. Even then, astronomers may only identify them as small overdensities of stars, not as clear, shining galaxies. If most of the galaxies in the universe are dwarfs, they may hold most of the information. This information is about how galaxies first form and evolve. The large galaxies like our own Milky Way have undergone many mergers and collisions. They have seen powerful bursts of star formation that have blurred their early history. The dwarfs, being smaller and simpler, often carry a more direct, pristine record. They record what happened billions of years ago. The universe is often described as a vast cosmic web. Galaxies are strung along the great filaments of dark matter. They are separated by vast empty voids. If the dwarfs truly dominate the numbers, then these filaments are even richer and more complex. They are more complex than we had once thought. Each faint dwarf adds a little more weight to this cosmic scaffolding. It helps us to map the invisible skeleton of dark matter that holds everything together. Without accounting for them, our picture of the universe is fundamentally incomplete. Looking ahead, astronomers expect this hidden majority to finally step into the light. This will happen as new and more powerful tools become available. Telescopes like the Vera C. Rubin Observatory are expected to reveal hundreds of new dwarfs. With its ability to survey wide areas of the sky in great depth, it will find them. It will see them around the Milky Way and beyond. Space-based observatories will also be able to peer deeper. They are freed from the blurring effects of the Earth's atmosphere. They will detect the faint smudges of light that ground-based telescopes often cannot. The missing satellites problem. In the late 20th century, astronomers began to run large and complex computer simulations. They wanted to understand how galaxies first formed. These simulations used the known laws of physics. They also used the idea that dark matter makes up most of the universe's mass. Out of this work came a striking and beautiful picture. Galaxies like our own Milky Way should not be alone. They should be surrounded by hundreds and maybe even thousands of small dark matter halos, many of which ought to host dwarf galaxies. In other words, our galaxy should have a massive swarming retinue of tiny companions, like bees around a hive. But when the astronomers looked into the real sky, they saw something very different. Instead of hundreds of companions, only a few dozen satellite galaxies were known at the time. This stark mismatch became known as the missing satellites problem. It was a mismatch between the theoretical prediction and the actual observation. The problem stands out because the same simulations reproduce the large-scale cosmic structure. They do so with an impressive, almost breathtaking accuracy, but they fail at small scales. The cosmic web, the clustering of the galaxies, the growth of the large halos, all of it matches. It matches what we see in the real universe. But at the small scales around individual galaxies like our own, the numbers simply do not add up. The dark matter halos that should exist in great numbers seem to be empty. Either they exist but do not host any galaxies, or our understanding of dark matter itself is fundamentally incomplete. At first, some astronomers wondered if the problem might be a simple one. Perhaps the missing satellites were really there, but perhaps they were just too faint for our telescopes to detect. As digital surveys and deeper imaging came online, more faint dwarfs began to appear. They appeared around the Milky Way. The Sloan Digital Sky Survey, for instance, uncovered many ultra-faint dwarfs. Later surveys, like the Dark Energy Survey, found more in the south. Each new discovery chipped away at the missing satellites problem. Yet even today, the total number of known dwarfs around the Milky Way is still in the dozens. This is far, far fewer than the hundreds that are predicted by the simplest models. If the satellites are not simply hiding, then another possibility exists. Perhaps the simulations assume too much about how gas and stars behave in small halos. In theory, every single halo should be able to collect gas and form stars, but in practice many of them may fail to do so. In the early universe, powerful radiation may have blasted away the gas from small halos, radiation from the very first stars and quasars. This could have happened before they could form any galaxies. Later, supernova explosions inside the early dwarfs could have blown out much of their gas. This would have shut down star formation permanently. If this happened often enough, then many of the dark matter halos might be truly dark. They would contain no stars at all and therefore be completely invisible to our telescopes. In this view, the missing satellites are not truly missing. They are there, but they never manage to light up. Another angle is that the physics of dark matter itself may not be what we think it is. The standard model assumes that dark matter is cold. This means it moves slowly and clumps together very easily. This cold, dark matter model predicts lots of small halos. These are just the kind that lead to the missing satellites problem. But what if dark matter behaves differently? If dark matter is warm, moving faster in the early universe, it would smooth out small structures. This would prevent as many dwarfs from forming. If it can also interact with itself in subtle ways, it might further erase the smallest halos. These alternatives to the standard model remain speculative, but the missing satellites problem is one of the strongest motivations for scientists to explore them. The Milky Way's satellites are not the only place to test this issue. In Andromeda too, the numbers fall short of the predictions, although it seems to have slightly more companions than the Milky Way does. Looking at clusters of galaxies provides another test. In these larger, more crowded environments, the small galaxies seem to be more abundant, but the smallest of the predicted dwarfs are still very hard to find. Across all of these different scales, the same basic puzzle repeats itself. The missing satellites problem blends two different mysteries. On the one hand, it might be about how galaxies form. Maybe star formation shuts down in small halos more often than we had thought. On the other hand, it might be about the nature of dark matter itself. Maybe the invisible substance we rely on in our models has properties we haven't uncovered. The challenge for scientists is to separate these two possibilities. If we can detect more ultra-faint dwarfs, we might confirm that many small halos host galaxies. If we cannot, then we may need to rethink the very nature of dark matter itself. In recent years, some progress has been made by carefully mapping the sky. Astronomers have been looking for stellar streams. These long, ghostly streams show that some satellites have come and gone over billions of years. This means that the Milky Way's current census of dwarfs is not the whole story. Over the billions of years, many more may have existed, only to be absorbed or destroyed by the host galaxy. If so, then the simulations may not be entirely wrong after all. Still, even after accounting for faintness and destruction, the gap remains wide. The gap between theory and observation. Some estimates suggest that the Milky Way should have at least a few hundred satellites. Unless our surveys are missing nearly all of them, we are left with a serious, persistent tension. This is why the missing satellites problem is a crucial test of the standard model of cosmology. If our picture of the universe is correct, the missing satellites must be out there, somewhere waiting to be found. The missing satellites problem forces astronomers to test the absolute limits of their models and to look more carefully at the smallest, faintest scales of the universe. Whether the answer lies in the faint galaxies we have not yet seen, in a new kind of physics we do not yet understand, or in a subtle mix of both, the puzzle itself helps to drive the research forward. How dwarf galaxies are discovered. One of the earliest ways to find a dwarf galaxy was to simply stumble across it by accident. A careful astronomer might notice a faint, hazy smudge on a photographic plate, a smudge that didn't quite match a known star cluster. These early discoveries were often uncertain. The difference between a loosely bound group of stars and a true galaxy is very difficult to see, not at a single glance. But as instruments improved and digital imaging replaced old film surveys changed, astronomers began to design surveys that specifically looked for such faint, smudge-like objects. The wide-field surveys became an essential tool. They allowed the entire sky to be mapped with enough detail to capture even the faintest structures. The Sloan Digital Sky Survey, or SDSS, was one of the most important steps forward. Using a dedicated telescope, it scanned large parts of the sky with high precision. It produced one of the most complete, detailed maps of the stars and galaxies ever made. Within this vast, rich dataset, researchers began to notice subtle overdensities of stars. These were tiny patches of the sky where more stars appeared than were expected. These overdensities often turned out to be the faint, hidden dwarf galaxies. What was once completely overlooked was suddenly made visible. This was thanks to careful statistical analysis of enormous amounts of digital data. The star counts became one of the primary methods of discovery. Instead of looking for a single glowing patch of light, astronomers would search for regions where stars seemed to be unusually concentrated. A dwarf galaxy might only reveal itself as a slight bump in a star count graph, but with enough data and careful analysis, these bumps are clear fingerprints of hidden companions. This method is particularly powerful when used near the Milky Way. Our own galaxy contains billions of stars. This makes the background sky very crowded and noisy. But when a dwarf galaxy is present, the stars in that patch often share similar properties such as their color or their brightness. Astronomers can filter for stars that appear to be older, redder, or dimmer. These are the very characteristics typical of dwarf galaxy populations. By doing so, they can pull a faint galaxy out of the overwhelming glare of the Milky Way. The ultra-faint dwarfs discovered in the past 2 decades contain very few stars. They are on the very edge of what we might even consider to be a galaxy at all. Detecting such objects requires not just powerful telescopes, it also requires clever, sophisticated techniques to filter the signal from the noise. The faintness of these dwarfs means that if you were standing inside one, you might not realize it. You might not even realize you were in a galaxy at all. The stars would be too sparse, and the night sky would not be much different from what you would see on Earth. To uncover such fragile, ghostly systems, astronomers now rely on deep surveys. These go far beyond the sensitivity of earlier projects. The Dark Energy Survey has been one of the most successful at finding these new dwarfs. Carried out using a 4-meter telescope in Chile, it has revealed dozens of them. By imaging large areas of the southern sky to an extreme depth, it found ultra-faint dwarfs. These dwarfs are orbiting the Milky Way. Modern instruments also make use of motion to confirm the discoveries. A random patch of stars could easily be mistaken for a dwarf, but true galaxies have stars that are moving together bound by a shared gravitational field. Astronomers can test whether a faint group of stars is truly a galaxy. They do this by measuring the tiny shifts in starlight caused by motion. This requires highly sensitive spectrographs. If the stars show random, unconnected motions, the group might be a chance alignment. It might be just a star cluster, but if they move in a way that suggests they are bound by an invisible mass, then the presence of dark matter reveals it to be a galaxy. The Hubble Space Telescope has been used to resolve the individual stars in suspected dwarfs. This allows astronomers to measure their ages and to confirm their nature. With its sharp, clear vision high above the Earth's atmosphere, Hubble can distinguish details that ground-based telescopes often blur together. Future telescopes promise to revolutionize this search even further. The Legacy Survey of Space and Time, or LSST, will repeatedly scan the sky. It will provide a dynamic living map that can reveal not only faint galaxies, but also how they change over time. The process of discovery is a slow, patient, and ongoing one. But with every faint smudge that is revealed, the cosmos becomes a little clearer. The hidden, intricate structure of the cosmos, mapping the Milky Way's neighborhood. Around the Milky Way, there swarm dozens of smaller companions. These satellites vary enormously in their appearance, their structure, and their size. Yet together they paint a rich, detailed picture of how diverse the galactic family truly is. The most obvious members of this family are the Magellanic Clouds. The Large Magellanic Cloud, or LMC, is so bright it can be seen with the naked eye. This is from the southern hemisphere. With roughly 30 billion stars, it is by far the largest of the Milky Way's companions. Its smaller sibling, the Small Magellanic Cloud, or SMC, contains only a few billion stars, but it still easily outshines nearly all of the other dwarfs in our cosmic neighborhood. Both of them are irregular galaxies. They lack the clear, elegant spirals or the smooth, glowing ellipses of giants like the Milky Way. They are filled with gas and are actively forming new stars. And they display brilliant regions of glowing nebulae where stellar nurseries flourish. These two galaxies are the true heavyweights of the Milky Way's entourage. Their mutual interaction makes them among the most studied objects in the entire sky. An interaction with each other and with the larger galaxy. Beyond them, there lies a retinue of smaller, more fragile systems. These are the dwarf spheroidals, so faint they remained hidden until quite recently. They are ghost-like, often containing only a few 100,000 stars. These stars are spread out over large volumes of space. Unlike the Magellanic Clouds, they hold very little or no gas. And any new star formation is completely absent. Examples of these include the Sculptor, the Fornax, and the Carina dwarfs. Each one is a dim, faint collection of ancient stars. They orbit at distances of tens to hundreds of thousands of light years away from us. Still closer to the Milky Way, some of the satellites creep almost unnoticed through its vast halo. The Sagittarius dwarf was discovered only in the 1990s. It is currently being torn apart as it plunges through the very disk of our own galaxy. Long, ghostly stellar streams arc across the sky. They mark its remains as it is steadily, relentlessly digested by the larger galaxy. The Canis Major dwarf, another low-mass companion, is similarly in the process of dissolution. Its stars are smeared out into great arcs that wrap around the Milky Way's outskirts. These galaxies are powerful reminders that the boundaries of a galaxy are porous. The census of the satellites extends even farther. It stretches hundreds of thousands of light years out from the Milky Way's center. Some of the companions, like Leo I and Leo II, orbit at great distances. They are almost on the very edge of the galaxy's sphere of influence. Despite their remoteness, they still remain tied to the Milky Way's gravity. They trace their slow, patient orbits over billions of years. Each of these systems adds a different chapter to the galactic family's history. Some of them show evidence of ancient, powerful bursts of star formation. Others display a smooth, calm population of only old ancient stars. The satellites can be grouped not just by their brightness or their size, but also by their type. The gas-rich irregulars like the Magellanic Clouds are rare but spectacular. The gas-poor spheroidals are numerous, faint, and widely dispersed. The ultra-faint dwarfs push the very definition of a galaxy to its absolute edge. Together, they outline a rich spectrum of the different kinds of companions. Another important way to look at our cosmic neighborhood is by the distance. A few of the dwarfs lie very close, only tens of thousands of light years away. They are deep inside the Milky Way's halo. Others drift far beyond at distances closer to 1 million light-years. Here, the pull of the Milky Way competes with that of the Andromeda Galaxy. The distribution is not even. Clumps of the satellites appear in certain regions. They possibly trace the remnants of larger systems that broke apart long ago. Some researchers even argue that the satellites may be arranged in vast, thin plains or streams, although whether this is real or just an illusion is still a matter of heated debate. The Magellanic Clouds are the giants with their billions of stars each. The classic spheroidals contain millions of stars. The ultra-faints may have only hundreds or thousands. Yet across this wide range of sizes, all of them are considered to be galaxies. By charting the Milky Way's neighborhood in this way, astronomers can build a picture of not just what exists today, but also of the history of the interactions. The bright irregulars may represent fresh arrivals not yet stripped of their gas. The faint spheroidals may be the remains of systems battered by the Milky Way's tides. Some ultrafaints may be the fossils of the very first galaxies that formed in the universe. They are preserved in a miniature form. Each companion offers a clue to how galaxies grow. Stellar streams the ghostly trails of consumed galaxies. If one could strip away the bright glare of the Milky Way's disk and look only at its vast halo, the sight would not be smooth or empty. Instead, it would resemble a giant spider's web woven from the stars themselves. It would be thin and delicate, but stretching over immense cosmic distances. These are the stellar streams. They are not whole systems anymore. They are the shredded remains of dwarf galaxies and star clusters, systems that were once proud and independent, but they have been torn apart by the relentless gravitational pull of the Milky Way. Their stars have been pulled free and stretched out into long, graceful arcs. The Milky Way's halo is filled with them. It's like a cosmic graveyard of companions that could not resist the pull of the giant at the center. Imagine a small galaxy falling into the Milky Way. Its stars are moving together, bound by their own mutual gravity. But as it circles the larger galaxy, the powerful tidal pull begins to stretch it. The stars on the far side feel a slightly weaker tug. Meanwhile, those on the near side feel a stronger one. Over time, the entire system unravels its stars, peeling off and forming long, trailing tails. These tails follow the original orbit of the lost galaxy. They wrap around the Milky Way in long, faint trails. These trails can span hundreds of thousands of light years. What was once a single coherent body becomes a dispersed, ghostly ribbon. It is impossible to separate from the greater halo, except by the most careful of observations. One of the most famous of these is the Sagittarius stream. It is the debris of the Sagittarius dwarf galaxy. Its stars form great arcs that wrap almost entirely around the Milky Way. Other streams like GD1, the Orphan stream, and the Palomar 5 stream are equally striking. Though they are often much fainter, some of them are linked to disrupted dwarf galaxies. Others are linked to globular clusters that were pulled apart. Each one is a fossil record written in the positions and the motions of the stars. By studying them, scientists can retrace the orbits of these vanished systems. They can reconstruct the long, violent history of the Milky Way's growth. Detecting them is a significant challenge. Many of them are incredibly faint, lost in the vast sea of background stars. But the surveys that map the entire sky in great detail have revealed more and more of them. What once seemed completely invisible has now become a clear pattern. A pattern that can be traced and measured. As they orbit the Milky Way, they are shaped not just by the visible matter. If the dark matter halo were perfectly smooth, the streams would be graceful and unbroken. But some of them appear to be clumpy, torn in places where stars have been deflected. These disruptions may reveal the presence of invisible dark matter clumps, the remnants of smaller halos that never formed into galaxies. In this way, stellar streams act like giant cosmic detectors. They map the unseen structure of our galaxy's dark matter through their own distortions. Even after a dwarf galaxy has been completely consumed, its stars do not simply vanish. They continue to move together, sometimes for billions of years. Over time, the stream thins out and disperses. It blends into the halo until it can no longer be distinguished. But before that final dissolution, it offers a precious glimpse into a violent past. Some astronomers describe the Milky Way's halo as a vast archive. The stellar streams are the documents contained within it. Taken together, they show that the Milky Way grew layer by layer, piece by piece. It grew by consuming its smaller neighbors. Without the streams, this long history might remain completely hidden from us. The Orphan Stream is one example of a particularly evocative case, as its very name suggests the parent system that created it has been almost entirely destroyed. It left behind only the faint ribbon of its stars. Astronomers can measure the motions of these stars and deduce the orbit of the lost system. But the original dwarf galaxy is no longer identifiable. It has been erased, leaving behind only its ghostly trail. The Palomar 5, on the other hand, still has a surviving core. It's a globular cluster that continues to shed its stars into a long pair of tidal tails. The observations show that it is slowly dissolving, and in time it too will vanish, leaving behind only its stream as a memory of its existence. Some of the streams are twisted and folded, reflecting a complex, chaotic history. A system might orbit many times, and each pass would stretch new stars out into the halo. The overlapping arcs can make the structure seem chaotic, but a careful study can reveal the rhythm of the repeated disruptions. These patterns not only map the past interactions, they also allow astronomers to test their models of the Milky Way's formation. In a sense, stellar streams are evidence of a continuity. The dwarf galaxies and clusters that birthed them no longer exist in their original forms, yet their stars live on, circling the galaxy as part of a new, larger whole. The Milky Way's brightness, its richness, is due in part to these absorbed companions. Without them, it would be a smaller, less grand galaxy. The large Magellanic Cloud, a satellite that rivals a galaxy, with its broad, sprawling spread of stars, and its active regions of star formation, and its noticeable spiral-like features, the LMC looks more like a scaled-down spiral galaxy. It doesn't look like a minor satellite that is tagging along. For observers in the southern hemisphere, it stands out to the naked eye. It is visible as a cloudy patch in the night sky. It has been known to humans long before telescopes were ever invented. Its brightness and structure make it one of the most remarkable examples of a companion galaxy, and one of the most studied as well. Its estimated stellar mass is around 1/10 that of the Milky Way. This means that it is enormous by the standards of satellite galaxies. It also appears to contain a large halo of dark matter. This allows it to hold itself together even as it passes close to the Milky Way. That stability has allowed it to keep an organized structure rather than being torn apart. Astronomers can trace the way its stars form patterns across the sky. There is clear evidence of spiral arms and a central bar of stars. These are much like those seen in galaxies that are far larger. This is one of the reasons why the LMC occupies such an unusual place in the galaxy family. It seems to straddle the line between being a true independent galaxy and a bound satellite, a satellite bound to our own. The star formation is happening at a rapid pace. This is compared to many other nearby galaxies, including our own. One of the most famous star-forming regions in the entire sky sits within its bounds, the Tarantula Nebula. This nebula is a sprawling, glowing cloud of gas and dust where new stars are being born. The brightest and most massive stars that are known have been found inside it. They shine with such power that they illuminate the entire region. Supernovae have also been observed within the LMC, their explosions lighting up its skies. In 1987, the closest supernova visible to Earth in modern times occurred in the LMC. This gave astronomers an unparalleled chance to study how such an event unfolds in detail. That single explosion, known as SN1987A, remains one of the most important astronomical events, one of the most important of the past century, and it happened right inside this remarkable galaxy. Many small galaxies have lost their gas, but the LMC still has large reserves of hydrogen. This provides the raw material for stars to keep on forming. This supply of gas may be partly due to its size and partly due to its orbit. Its orbit has only recently brought it close to the Milky Way. Some studies suggest that the LMC is on its first close pass around our galaxy. This means it has not yet had time to be fully disrupted by the Milky Way's tidal forces. If this is true, then we are catching the LMC at a special moment in its history, just as it begins to feel the grip of a larger neighbor. For years, astronomers assumed that the LMC had been circling the Milky Way for billions of years. They assumed it had completed many orbits, but more recent measurements of its velocity suggest it may be moving too quickly for that. Instead, it might have only recently fallen into the Milky Way's sphere of influence. Perhaps it brought along its own smaller companions. If that is correct, then the LMC is more like an intruder than a long-term partner. It is a separate galaxy that is only now becoming a satellite. The LMC's gravity is strong enough to tug on the Milky Way itself. It shifts the motions of the stars in our galaxy's disk. Some astronomers believe that the Milky Way's dark matter halo may even be distorted by the LMC's pull. The interaction between the two galaxies has also left behind a vast trail of gas. This is called the Magellanic Stream. This ribbon of material stretches across much of the sky. It was stripped from the LMC and the small Magellanic Cloud by gravitational forces. The stream may one day rain down onto the Milky Way. This could fuel new bursts of star formation in our galaxy. If the Milky Way was smaller or the LMC was farther away, we might classify it differently. The fact that it lies in this grey zone shows how nature resists simple categories. The galaxies, like all cosmic objects, exist on a spectrum. For humans on Earth, the large Magellanic Cloud has long been more than just a scientific puzzle. Navigators and storytellers in the Southern Hemisphere wove it into their traditions. Today, with telescopes and satellites, we can explore its depths in detail, but it still carries that same sense of wonder. It is a galaxy that is both near and foreign. The small Magellanic Cloud torn between the giants. The small Magellanic Cloud, or SMC, is an unusual companion. It doesn't have the neat spiral arms of a disk galaxy, nor does it have the smooth glowing light of an elliptical. Instead, it looks disordered and lopsided. It looks more like a patch of scattered light than a carefully built system. Over time, the picture that has emerged is that the SMC is not living in calm isolation. It is caught in a tug-of-war between two giants, the LMC and the Milky Way. Its strange appearance is a direct result of being pulled in different directions at once. The SMC is located about 200,000 light-years away from the Earth. That's close enough in cosmic terms to make it one of the nearest galaxies outside the Milky Way. It contains only a few 100 million stars, far fewer than its larger sibling. This means that the SMC is a small galaxy even by dwarf standards. Because it is so close, astronomers can watch how its star's gas and shape are changing. They change as forces from the outside pull on it. Instead of being a clean sphere or a disk, it stretches in an irregular pattern. Regions of dense stars are separated by gaps of empty space. One area looks like a main body, while another looks like a detached wing. It is as if a piece of the galaxy has been stretched away. This structure is believed to be the result of tidal forces. The two Magellanic Clouds are close enough that they form a pair. They orbit the Milky Way together. For billions of years, they have likely been circling each other, all while slowly spiraling inward toward our galaxy. Their mutual gravity binds them, but it also distorts them. The SMC, being the lighter of the two, is the one most obviously bent out of shape. Astronomers think that the wing-like extension of the SMC is the result of a close encounter. A close encounter with the LMC stripped away part of its material and left it trailing. Another clue to the SMC's struggles comes from its gas. When telescopes look at the Magellanic Clouds in radio light, they reveal a massive river of gas. This river is stretching away from them. This Magellanic Stream arcs across the sky for hundreds of thousands of light years. It is thought to have been pulled out of the SMC and the LMC. This happened during their repeated encounters with each other and the Milky Way. The SMC, with its lower mass, has lost more of its gas than the LMC. This is one of the reasons why the SMC looks so patchy today. The tidal pulling has also influenced how stars are born inside the SMC. Normally, star formation in a galaxy depends on the availability of cold gas clouds. In the SMC, astronomers see evidence of starbursts in its recent history. Some regions contain clusters of very young, bright stars. This indicates that the gravitational stress has sparked new activity. At the same time, other areas appear to be depleted. It's as if the fuel for star formation has already been swept away. This uneven pattern fits well with the picture of a galaxy caught in an ongoing struggle. Because it is nearby, scientists can measure its stars and gas in detail. They can even track how some of its stars are moving through space using precise instruments. These measurements show that the SMC is not simply drifting quietly around the Milky Way. Instead, it has a complex orbit. The irregular shape could be a sign that it is still adjusting to life under the Milky Way's pull. Astronomers debate whether the SMC and the LMC will eventually merge with each other. This would be before being absorbed into the Milky Way. If they merge, the combined system may resemble a larger dwarf galaxy, though it would still be far smaller than the Milky Way. If instead the Milky Way's gravity tears them apart first, the SMC may eventually dissolve. It would leave its stars scattered across the sky as streams and clusters. Either way, its current irregular form shows that it is already well on its way to being reshaped. Like its larger sibling, it appears as a fuzzy cloud of light, visible to the naked eye. This is on clear nights. Sailors once used it for navigation, and observers noted its unusual hazy appearance centuries before telescopes revealed its true nature. The SMC is a living example of what happens when small systems are caught between giants. They are reshaped by forces they cannot escape. The Magellanic Bridge and stream the tidal scars in the sky. The Magellanic Bridge is a structure of stars and gas that physically connects the LMC and the SMC. It is almost like a tether between them. For a long time, the clouds were thought of as two separate neighbors, drifting near the Milky Way, but observations in the 20th century revealed that they were bound together. The gravitational pull between them had drawn material out of the SMC. This material was drawn into the space between the two. When astronomers looked more closely, they saw streams of young blue stars. These stars were stretching across this gap. This showed that star formation had even taken place in this bridge. It was sparked by the compression of gas as it was torn out and reshaped. The Magellanic Bridge is a snapshot of motion. It is material caught in the middle of being traded and stripped during a long, ongoing encounter. An even more striking feature is the Magellanic Stream. Unlike the bridge, which sits between the clouds, the stream extends far beyond them. It wraps across the sky behind the pair as if they were dragging a comet's tail. This stream is made of hydrogen gas stretched out over more than 600,000 light-years. This is longer than the Milky Way itself. It is faint and invisible to the naked eye, but radio telescopes tuned to the frequency of neutral hydrogen can detect it clearly. The Magellanic Stream tells the story of repeated tidal encounters. These are encounters between the clouds and the Milky Way. Each time the dwarfs swing around, some of their gas is pulled loose. It is left trailing behind in space. Over billions of years, this has created a ribbon so vast it circles much of the southern sky. Gas is the fuel for star formation. When galaxies lose too much of it, they stop making new stars and slowly fade away. The stream suggests that the Magellanic Clouds cannot keep their material forever. In time, much of what once belonged to them will fall into the Milky Way. This will feed its halo and perhaps spark bursts of new star formation within our own galaxy. A fascinating aspect of these tidal features is that they are not uniform. The bridge and the stream show knots, clumps, and filaments. It's as if the forces pulling on them were not steady but chaotic. Some parts of the stream appear to be denser, while others fade into nothingness. The reasons for this are still being explored. Part of it comes from the uneven gravity of the Milky Way, which does not pull evenly. Part may also come from the interaction of the stripped gas with a thin atmosphere. This is an atmosphere of hot plasma that surrounds our galaxy, known as the circumgalactic medium. As the Magellanic gas moves through this halo, it is stretched, twisted, and even eroded. This leaves behind a ragged pattern rather than a smooth arc. In the distant universe, astronomers often see galaxies that are merging or tearing at each other, but those are usually so far away that only the broadest structures are visible. Here in our cosmic backyard, we can map the stripped gas almost cloud by cloud, star by star, and we can use it to test our models of how gravity and tidal forces work. This happens over millions of years. The bridge shows us what happens when two dwarf galaxies pass close enough to exchange matter. The stream shows what happens when those same dwarfs fall into the sphere of a much larger host. Together, they are like a laboratory of cosmic dynamics. They are visible not with exotic equipment, but with radio dishes and patient mapping. With instruments like the Australia Telescope Compact Array and the Parkes Radio Telescope, and space observatories such as Gaia, the details of the bridge and stream are becoming sharper. By tracking the motions of stars within the bridge, researchers can reconstruct history, the history of when the clouds last passed closest to one another. By measuring the chemical makeup of the stream, they can determine where the gas came from. Did it come mostly from the small Magellanic Cloud, the large, or a mix of both? These questions matter because they tell us not only about the fate of the clouds themselves, they also tell us about the long-term flow of matter into the Milky Way, the Sagittarius dwarf galaxy, a victim of cannibalism. The Sagittarius dwarf galaxy is a fragile system caught in the grip of the Milky Way's gravity. And unlike the Magellanic Clouds, which still hold together, the Sagittarius is being torn apart. It is a living demonstration of galactic cannibalism. Astronomers first recognized the Sagittarius dwarf in the 1990s, and even then, it was already showing signs of distress. Its stars were stretched out in long, faint streams that wrapped around the Milky Way, like a necklace that was broken apart and scattered across the sky. Instead of being a neat, compact ball of stars like many other dwarfs, the Sagittarius was elongated and shredded. It was caught in a process that has been going on for billions of years. The fact that it was discovered so late shows just how faint it had become. Much of its original mass is no longer bound to the galaxy itself. It has been stolen and spread throughout the Milky Way's halo. The story of the Sagittarius begins with its orbit. Unlike a quiet companion that circles far away, this dwarf plunges directly through our disk. This is a path that guarantees repeated encounters. Each pass subjects it to powerful tidal forces. As the Sagittarius swings past, the Milky Way's gravity pulls harder on its near side. It pulls harder on its near side than its far side. This slowly pries the stars and gas away. With every orbit it loses more of itself. It peels away layer by layer until only a small core remains. This violent process leaves scars that are visible across the night sky. The stellar streams from the Sagittarius wrap around the Milky Way like a ribbon wound around a globe. These streams are not just beautiful, they are scientific treasure troves. They act as test particles tracing the shape of the Milky Way's gravitational field. By mapping where the stars go, astronomers can infer the unseen distribution of dark matter. This dark matter gives the Milky Way most of its mass. In this way, the death of the Sagittarius provides a gift, a way to study the structure of our own galaxy. Some studies suggest that its repeated plunges may have triggered star formation bursts within our galaxy. As it passed through, it may have stirred up clouds of gas. It may have compressed them until they collapsed into new stars. If so, then the legacy of the Sagittarius is not only in the stars it lost, but also in the stars it helped to bring to life within the Milky Way. The relationship is parasitic and creative at the same time. The Sagittarius is not the first dwarf galaxy to meet such a fate, and it will not be the last. The Milky Way's halo is littered with the remnants of past meals. The faint streams of stars that once belonged to other small galaxies or clusters. Each stream tells a story of a past encounter. But the Sagittarius is unique because we are watching its destruction happen in real time. It is a rare case where the drama unfolds in the present. It gives astronomers a front-row seat to galactic cannibalism. What remains of the Sagittarius today is a faint core. It is orbiting about 70,000 light-years from the center of the Milky Way. It is still recognizable as a galaxy, but only barely. Compared to its likely original size, it is a shadow of itself. Its stars have been redistributed across the sky. Some of them are now indistinguishable from those born in the Milky Way. Over time, the core will continue to shrink until even that is gone. It will be completely consumed by the larger galaxy it orbits. How many of the Milky Way's stars were stolen rather than born within it? How many ancient dwarfs were swallowed long before we could trace their remains? And how does this steady diet of smaller companions shape the growth of galaxies like our own? In the Sagittarius, we see one of the answers unfolding, but the broader picture is that this is how galaxies grow. They consume their neighbors, merging and blending until their histories are inseparable. The Milky Way itself will one day merge with the Andromeda Galaxy. This will be an event on a far grander scale, but it will be built on the same principles at work in the Sagittarius's demise. The streams of stars from this small dwarf are the first hints of what happens. What happens when two galaxies cannot resist each other's pull? The Fornax dwarf a galaxy that is rich with globular clusters. The Fornax dwarf spheroidal galaxy is a quiet and unassuming companion to the Milky Way. It drifts some 460,000 light-years away. It is in the southern constellation of Fornax. At a first glance, it looks like any other dwarf, faint, diffuse, and easily lost against the dark. Yet it carries a secret that makes it stand out among its peers. The Fornax is home to not just one or two globular clusters, but at least 6 of them. For such a modest galaxy, this is extraordinary. The presence of so many globulars raises questions about how a system like Fornax came to be and what its history can tell us about the balance between survival and destruction, the balance in the lives of the dwarfs. Globular clusters are often thought of as the hallmarks of large galaxies. The Milky Way hosts more than 150 of them. Each one is a dense ball of hundreds of thousands of stars. These stars are bound together for billions of years. These clusters tend to be old, with stars that formed near the dawn of the galaxy. Their very presence speaks of long histories, and it speaks of the ability to hold on to gas and material in the early universe. The Fornax's 6 globular clusters are a surprise. This is because dwarf spheroidals are generally thought to be fragile. They lack the gravity and mass to gather and keep such star cities. Yet here is a small galaxy holding a collection of clusters that rivals some mid-sized galaxies. It has no more than a few billion solar masses at most. The clusters themselves orbit at various distances around the Fornax dwarf. They are scattered like tiny jewels around a dim lantern. Some of them lie close to the galaxy's core. Others drift far enough that they seem on the edge of breaking free. Astronomers have studied them closely because their stars preserve fossil-like records of past conditions. Many of the clusters contain stars that are more than 10 billion years old. This means that they formed early in the history of the universe. Their survival inside Fornax suggests that the galaxy may have once been richer. Though faint today, it may have held more gas and experienced bursts of star formation. Bursts that gave rise to these ancient populations. Unlike the Sagittarius dwarf, which is being pulled apart in long streams, the Fornax shows signs of being relatively stable. Its stars are not being stripped away in great numbers, and it has managed to hold on to its globular clusters. This hints that Fornax occupies a more favorable orbit. It is far enough from the Milky Way's gravitational claws to avoid immediate destruction. Located at nearly 500,000 light-years, it circles the Milky Way at a comfortable distance. A distance where the tides are weaker and the galaxy can preserve its structure. This isolation may be the reason why it has managed to keep its unique set of clusters and why it has kept them for so long. But why does Fornax have so many globular clusters? That question continues to puzzle astronomers. One possibility is that Fornax was once more massive. It may have had a deeper well of dark matter and more raw material. If the galaxy began its life larger and has since lost much of its outer material, the clusters we see today might be remnants from a more active past. Another idea is that Fornax captured some of its clusters during interactions with other small galaxies. In the crowded environment of the Milky Way's halo, galaxies occasionally brush past each other. They exchange stars or even swallow smaller companions. Perhaps Fornax was in the right place at the right time. It was in the right place to gather and keep more than its share. The clusters also tell us something important about the dark matter halo surrounding Fornax. To keep globular clusters in orbit for billions of years, a galaxy must have a stable field, a stable and extended gravitational field. If Fornax were made only of its visible stars, the clusters would have likely drifted away. They would have drifted away long ago. Their continued presence is evidence of a larger unseen structure anchoring them in place. Astronomers have also noticed that the globular clusters of Fornax may not perfectly match the galaxy. They may not match its own star population. The clusters are typically older and more metal-poor. This means their stars have fewer heavy elements compared to the more central stars of Fornax. This suggests that the galaxy had multiple episodes of star formation. First, an early rapid burst produced the clusters. Then a slower period where gas cooled and formed the younger stars in its core. The clusters may be the survivors of that first era, carrying the memory of Fornax's youth. The main body of the galaxy reflects the later stages of its life. The Fornax's unique combination of stability and richness has made it a favorite target. Both ground-based observatories and space telescopes have mapped its stars. They are trying to piece together its story. Deep images reveal layers of stellar populations, from the oldest red giants to relatively younger stars formed only a few billion years ago. Unlike some dwarfs that seem to be frozen in time, Fornax appears to have continued forming stars well after its birth, though not at the furious pace of a larger spiral like the Milky Way. This extended activity may have played a role in its ability to host so many globular clusters. The contrast between Fornax and galaxies like Sagittarius shows how varied dwarf galaxies can be. Sagittarius, once larger, is being dismantled by the Milky Way's pull. It is leaving trails of stars across the sky. Fornax, more distant, has been left largely intact. Where Sagittarius is losing everything, Fornax has preserved treasures. Its clusters are like relics in a museum. They hint at an earlier, brighter time when the galaxy was more alive with star formation. Fornax is not as massive as the Magellanic Clouds, yet it is not as fragile as the smallest ultra-faint dwarfs. Its star-forming history is richer than some, but quieter than others. and its abundance of globular clusters sets it apart entirely. It challenges our ideas about how such systems form and survive. The sculptor and the sexton's dwarves. The sculptor and the sextons, both orbiting the Milky Way at moderate distances, are quiet companions. They illustrate a different side of galactic life, of slow evolution and long survival. The sculptor dwarf galaxy lies about 290,000 light-years from Earth. It orbits on the outer edges of the Milky Way's gravitational pull. It was discovered in 1937 by Harlow Shapley. He noticed a clustering of faint stars in the constellation of Sculptor. It is only visible through telescopes, and even then it blends easily with the foreground of the Milky Way's own stars. To the human eye, it is a faint smear of light, but in reality it is a spheroidal galaxy containing a few million stars. The galaxy hosts mostly old stars with very little evidence of recent star formation. Unlike, say, the LMC, which is still actively producing new stars, the Sculptor seems to have shut down that process billions of years ago. Its gas supply has either been stripped away or used up. This leaves behind only the fossil record of its past in the form of ancient stars. These stars are metal poor. That scarcity of metals suggests that Sculptor formed its stars early in the history of the universe. This was before multiple generations of supernovae could enrich the gas with heavier elements. The sextons discovered later in 1990 is even fainter and more elusive. It is more elusive than the Sculptor. Located around 320,000 light-years from Earth, it is among the dimmest galaxies. It is in the direction of the constellation Sextans. It has one of the lowest surface brightnesses known. To detect it, astronomers had to use careful counts of faint stars. This is because the galaxy itself is barely brighter than the background night sky. The Sextans is a true ghost of a galaxy. Like the Sculptor, it is a spheroidal dwarf. This means it has a roundish, puffed-up appearance. It has no spiral arms or disks that larger galaxies often display. Its star population is small, numbering in the hundreds of thousands rather than millions, but the stars it does have tell a similar story. Most of them are old, with little evidence of ongoing star formation. The Sextans, too, appears to have run out of gas long ago. It leaves behind only the quiet glow of ancient suns. The calm nature of these galaxies might at first glance seem dull. It might seem dull compared to the tidal streams of Sagittarius or the brilliant activity of the Magellanic Clouds, but because they are not being shredded apart or warped, they offer cleaner conditions for studying internal processes. Astronomers can look at their stars without worrying too much about recent disruptions. They can reconstruct a straightforward history of star formation. By comparing the metallicity of stars across different ages, researchers can trace something. They can trace how quickly Sculptor and Sextans enriched their gas with heavy elements. This happened before star formation shut down. The picture that emerges is one of galaxies that formed stars early. They experienced a brief period of chemical growth, and then they entered a long quiescence. This tells us that not every dwarf galaxy is destined for chaos. Some of them simply live quietly in the shadow of their host for billions of years. In cosmological simulations, small galaxies like Sculptor and Sextans are common. They are expected to be the most common building blocks of larger galaxies. These dwarfs merge together, and with bigger systems, they contribute their stars to the galactic halos. Studying the ones that still survive today helps to confirm if the simulations are right. The relatively simple nature of Sculptor and Sextans allows astronomers to compare them. They can compare them directly to the predictions of how gas should cool, form stars, and lose its fuel. If models can reproduce galaxies like these, then scientists gain confidence in their framework, their larger framework for galaxy evolution. If not, then perhaps something needs to be reconsidered. something about feedback from supernovae gas loss or dark matter. In many cases, dwarf spheroidal galaxies appear to have far more dark matter than normal matter. This makes them excellent test beds for the nature of this mysterious component. In fact, some of the strongest evidence for dark matter's presence comes from faint dwarfs like these, not from grand spiral galaxies like the Milky Way. The sculptor has another distinction that is worth noting. Its stars are arranged in a pattern that suggests two overlapping populations. Some of the stars are more centrally concentrated and slightly richer in metals. Others are more spread out and metal poor. This hints at a complex history. Perhaps it involved more than one burst of star formation or interactions that stirred its contents even within a galaxy that seems quiet. Subtle clues like this remind us that no galaxy is entirely uneventful. The sextans, with its extremely low density of stars, raises questions of its own. How did such a diffuse galaxy manage to form at all without being torn apart? And how has it avoided destruction by the Milky Way's tidal forces for so long? These puzzles keep astronomers returning to these faint smudges of light. Smudges that at first glance might seem unremarkable. Seen in the larger portrait of the Milky Way's satellites, sculptor and sextans represent a side, the understated side of the family. They do not boast sprawling bridges of gas, dramatic clusters, or obvious trails of destruction. Instead, they persist as dim but stable neighbors. Their value lies in their simplicity. The Ursa Minor and the Draco dwarfs the dark matter strongholds. If you were to look at the night sky without any aid, the Ursa Minor and Draco dwarf galaxies would never reveal themselves to you. They are invisible to the naked eye. They are only betrayed by the faintest sprinkling of stars. This is when astronomers use deep imaging and sensitive instruments. Yet, despite their quiet appearance, these two galaxies hide a vast amount of dark matter. It outweighs their stars many times over. In fact, when it comes to the ratio of visible matter to invisible mass, few systems are as extreme as Ursa Minor and Draco. The Ursa Minor dwarf galaxy lies in the northern sky. It is close to the famous constellation of the Little Dipper. If you could travel there, you would find a faint collection of old stars. Most of them formed more than 10 billion years ago. It has very little gas left today. This means that star formation shut down a long time ago. The Draco, its neighbor, is much the same. Named after the constellation of the Dragon, the Draco dwarf galaxy is also a tiny system. It coils across the northern sky. It is a faint system dominated by ancient stars. Both of them are classified as dwarf spheroidal galaxies. They are not undergoing any dramatic events, and on the surface they seem uneventful, but their true importance comes from what lies beneath. In Ursa Minor and Draco, dark matter dominates completely. Estimates suggest that more than 90% of their mass is made of dark matter. For every star that shines, there are countless invisible particles. These particles provide the real backbone of the galaxy. Their mass-to-light ratios are staggering, dozens, even hundreds of times greater than our galaxies. The Milky Way's ratio is much smaller. In other words, they are the strongholds of dark matter. In the Milky Way, dark matter is mixed with stars, gas, and dust in enormous quantities. This makes it hard to isolate. But in dwarfs like Draco and Ursa Minor, the picture is much cleaner. They are like magnifying glasses for dark matter physics. One of the big debates in cosmology is how dark matter behaves on small scales. The standard picture of cold, dark matter predicts that galaxies should have dense, cuspy centers. Here, dark matter piles up toward the core, but observations of systems like Ursa Minor and Draco sometimes suggest flatter profiles. They suggest chord profiles where the density of dark matter is more spread out. This has sparked discussions about whether our models of dark matter need to be revised, or whether processes like supernova explosions reshape the matter in these tiny galaxies. Another related puzzle is the too big to fail problem. In simulations of the Milky Way surroundings, many dark matter halos appear. These halos should be large enough to host bright dwarf galaxies. Yet when astronomers look around our galaxy, they don't find as many luminous dwarfs as expected. Some of the halos seem to be completely dark, invisible, but still predicted to exist. This raises questions about the efficiency of star formation in small halos, and about whether dark matter behaves in ways the standard model doesn't capture. These galaxies live close to the Milky Way, well within its halo of dark matter. Over billions of years, the pull of the Milky Way could have disrupted them, just as it is tearing Sagittarius apart. Yet Draco and Ursa Minor remain relatively intact, though stretched by tidal forces. Their endurance hints that their dark matter halos are dense enough to shield them. They act like anchors that keep the galaxies from being fully shredded. In simulations of the universe, small dark matter halos are expected to form first. Then they merge to build larger galaxies like the Milky Way. The dwarf galaxies today are thought to be the survivors of that early age, the building blocks that never merged. By studying Draco and Ursa Minor, scientists get a glimpse of what those structures looked like, what those original structures might have looked like billions of years ago. This was before the Milky Way became the giant spiral it is today. Both galaxies were first spotted in the 20th century. This happened through painstaking surveys of photographic plates. Today, with wide-field digital surveys, we can study them in far greater detail. We can map individual stars across their surfaces and even trace their extended halos. Yet they remain elusive, requiring long exposures and sensitive instruments to reveal their true nature. Despite their quiet appearance, Draco and Ursa Minor are not irrelevant side notes. They are central to some of the biggest mysteries in modern astronomy. They might look like nothing more than faint smudges in the sky, but beneath their faint light lies a story about the unseen mass that shapes everything we know. The Boötes and the ultra-faint dwarfs the ghosts of the galactic halo. If the large and small Magellanic Clouds are the bright, obvious companions of the Milky Way, then the Boötes dwarfs and the so-called ultra-faint dwarfs are their exact opposite. They are the barely visible, fragile things that often slip beneath the limits of telescopes. When astronomers discovered them, many wondered if they could even be called galaxies at all. They contain only a few thousand stars, sometimes only a few hundred. These stars are scattered across faint, ghostly structures. The Boötes dwarf galaxy was first detected in 2006. It gave astronomers their first real taste of what such ghostly companions looked like. Boötes, the brightest of the group, is still incredibly dim compared to galaxies like Fornax. The stars inside Boötes are some of the most chemically primitive that we've ever seen. After Boötes, there came Boötes 2, an even fainter neighbor. Boötes 2 is so small and so dim that some astronomers questioned its status. Should it be considered a galaxy at all, or just a stray star cluster? Its stars are spread widely, and the system shows signs of being tugged apart by the Milky Way's gravity. Yet even this fragile little structure carries secrets. By studying the motions of its stars, astronomers found that Boötes II contains far more mass than its visible stars could account for. This suggests that it too sits inside a bubble of dark matter. If this is true, then Boötes II is not simply a star cluster but a galaxy in its own right. A galaxy whose stars are hanging on thanks only to the invisible gravity of dark matter. These discoveries opened the floodgates. With deeper sky surveys, astronomers began to uncover more of these faint companions. These companions were scattered through the Milky Way's halo. They were given the name ultra-faint dwarfs, a fitting description of their ghost-like presence. Unlike brighter dwarfs, such as Fornax, the ultra-faints only appear in painstaking surveys. Surveys where astronomers carefully sift through billions of stars to find small clumps. clumps that share a common motion. Each new discovery added another faint, fragile point to the Milky Way's extended family. Many of their stars are thought to have formed more than 12 billion years ago. This was in the first wave of star formation after the Big Bang. Unlike larger galaxies which experienced multiple generations of star birth and chemical enrichment, the ultra-faints seem to have stopped forming stars very early. Their stars remain poor, in heavy elements frozen in a primitive state, a state that reflects the universe's earliest chemistry. Some of the most famous ultra-faints, like Segway 1, exemplify this. Segway 1 is so dim that it emits less light than a single bright star. For years, astronomers debated whether it could really be a galaxy or just a chance grouping, but its stars move in ways that suggest the presence of a hidden mass. Once again, this points toward dark matter. What makes Segway 1 extraordinary is the metallicity of its stars. These stars are among the most metal-poor in the entire universe. This marks them as survivors from the earliest epoch. In that sense, Segway 1 is not just a ghost of a galaxy. It is a fossil from the dawn of time. Another ultra-faint Reticulum 2 stunned astronomers. Its stars were found to be unusually rich in heavy elements created through rare neutron star mergers. This was unexpected because such tiny galaxies were thought to be too small to retain the products of such explosive events. Yet Reticulum 2 showed that even the smallest galaxies could bear witness to cataclysmic events. This adds new layers to the story of chemical evolution in the universe. Each ultra-faint dwarf seems to tell a slightly different story. Together, they sketch a mosaic of the early cosmos. Why do some dark matter halos host thriving galaxies while others end up as ghosts? The leading idea is that the smallest halos formed stars early, but then the universe changed. When the first generations of stars lit up, they flooded the cosmos with radiation. This radiation heated and stripped gas from the smallest galaxies. Star formation ceased, leaving only a sparse handful of old stars behind. In this view, the ultra-faint dwarfs are the survivors of a cosmic purge. They are the remnants of a time when only the largest halos could keep forming stars. They are also important because they test the predictions of cosmological models. Perhaps many more ultra-faints remain undiscovered, hiding in the faintest corners of the sky. Or perhaps not all dark matter halos are able to light up with stars. By searching for these ghostly galaxies, astronomers hope to bring theory and observation closer into agreement. The Canis Major overdensity, a galaxy or just a ripple? If you look toward the constellation of Canis Major, the greater dog in the sky, you will be staring into one of the most debated regions in our galactic neighborhood. Here lies what astronomers call the Canis Major overdensity, a concentration of stars that has stirred up arguments since it was first noticed. This happened in the early 2000s. Unlike the Magellanic Clouds or the Sagittarius Dwarf, its status is not clear. Is it truly a small galaxy being consumed by the Milky Way, or is it simply a ripple, a natural gathering of stars within our own galaxy's spiral disk? The Canis Major overdensity first came to attention through surveys that mapped the distribution of stars across the sky. Astronomers noticed that in the direction of Canis Major, there seemed to be an unusual clump of stars lying just beyond the Milky Way's thick disk. What made it especially interesting was that these stars appeared to follow their own path. This hinted at the possibility that they belonged to a separate structure. If this was true, it would mean that the Milky Way was devouring yet another dwarf galaxy. The excitement grew because this overdensity appeared to be relatively close to us, only about 25,000 light-years from Earth. This is closer than most other known dwarfs. The idea of a dwarf galaxy so near to us was thrilling. Just like the Sagittarius dwarf, which leaves long streams of stars as it's pulled apart, the Canis Major system seemed to offer evidence of being shredded by the Milky Way's powerful gravity. Observers claim to detect a structure called the Monoceros ring. This is a vast arc of stars wrapping around the Milky Way's disk. It could be the remains of tidal streams linked to Canis Major. To many, this was a strong sign that they were seeing another captured galaxy dissolving into our own. But as with many discoveries, the story quickly became more complicated. Some astronomers pointed out that the Milky Way's disk is not a simple flat sheet. Instead, it bends and warps with ripples and flares. These can create patterns of stars that look like overdensities from our vantage point. In this view, the stars in Canis Major might not belong to a separate galaxy at all. They could simply be part of our own galaxy's outer disk. They could be piled up in a way that makes them look distinct. What looked like the signature of an intruding dwarf might just be our galaxy's natural structure. It might just be confusing the picture. The debate between these two views, a galaxy or a ripple, has never been fully settled. Different studies have offered conflicting results. Some surveys have shown populations of stars in Canis Major that appear older and more metal-poor, fitting the profile of a dwarf galaxy. Others have found that the stars match the characteristics of Milky Way disk stars. This suggests that the overdensity is nothing more than a local bump in the galactic plane. The lack of a clear core or a defined center makes the case weaker compared to systems like the Fornax or sculptor dwarfs, which have their own identity. One of the difficulties is that the Canis Major region sits in a crowded part of the sky. Looking through the disk of the Milky Way means looking through countless stars, gas and dust. This heavy background makes it hard to sort out which stars belong to what structure. Unlike the Magellanic Clouds, which stand out plainly against the dark backdrop, the Canis Major blends into the Milky Way's glow. Untangling its identity requires careful measurements of star motions and chemical properties, and even then the results are not always decisive. If Canis Major is a true galaxy, it would mean the Milky Way has consumed yet another companion, and we would be catching it in the middle of the act. Its stars stretched out in the Monoceros ring would serve as a record of how galaxies grow, how they grow by accretion. The Milky Way's halo full of streams and faint remnants would gain another confirmed example, an example of stellar debris from a smaller victim. If, on the other hand, Canis Major is simply a ripple in the disk, the result is no less interesting. It would show that the Milky Way's own structure is more complex and dynamic than we once thought. The ripples and rings in the disk may be the scars of past encounters. Perhaps they were caused by dwarf galaxies plunging through the plane and disturbing the stars. In this case, Canis Major might not be a galaxy itself. It might be the footprint left by one, an echo of an older collision that shook our outer regions. This would tie the overdensity to the broader history of galactic interactions, even if it lacks its own identity. Even in regions relatively close to Earth, we are still discovering new structures, only tens of thousands of light years away, and we are struggling to understand their nature. The fact that astronomers cannot agree on whether this is a galaxy highlights something important. It highlights how fuzzy the boundaries can be. Galaxies are not always clear round islands of stars. They can blur into streams, rings, and overdensities. This makes it hard to draw a line between what counts as separate and what is part of the whole. The Canis Major does not need to be firmly placed in one category to be valuable. Its study sheds light on the processes that shape the Milky Way, whether through the steady settling of stars in the disk or the violent shredding of smaller galaxies. It occupies a grey zone, showing that our cosmic neighborhood is messy and dynamic. Perhaps newer tools will soon settle the debate. They might show once and for all whether Canis Major is a galaxy being consumed, or simply a quirk of the Milky Way's disk. Until then, it remains an object of fascination, a reminder that the boundary between galaxies and their hosts is not always clear, and that sometimes the most interesting discoveries lie in the in-between. The Gaia's galactic archaeology. The European Space Agency's Gaia mission was a spacecraft designed for a special purpose. It was designed not just to map where the stars are, but how they move. With Gaia, a new field has opened galactic archaeology. It is the study of the Milky Way's history, not by digging into the ground, but by tracing the motions of stars. It uncovers the hidden companions that were long ago swallowed by our galaxy. Gaia works by measuring parallax, the tiny shift in a star's position as the Earth orbits the Sun. This allows astronomers to measure distances with exquisite precision. But Gaia does more than that. It tracks proper motions, the slow drift of stars across the sky. It also tracks their radial velocities, the speeds at which they are moving toward or away from us. When combined, these measurements give a three-dimensional map, a map of how millions of stars are moving through the Milky Way. The sheer scale of the data has transformed how astronomers understand the galaxy's structure. Before Gaia, many of the Milky Way's faintest satellites and streams were essentially invisible. Their stars blended into the background. With Gaia, those same stars stand out. Their shared motions betray their common origin. One of the most dramatic discoveries from Gaia is the Gaia-Enceladus merger. This was not a dwarf galaxy drifting gently at the edge of the halo. It was a massive system, perhaps 1/4 the size of the Milky Way itself. It collided with our galaxy billions of years ago. The evidence came not from star counts. There was no clear overdensity of stars that shouted, "Here is a galaxy." It came from the motions. Astronomers noticed that a large group of stars in the halo moved on highly eccentric orbits. They were plunging in and out through the Milky Way. Their chemical makeup was also distinct, poorer in metals than the native stars of the disk. Put together, it told a story of a great collision, a collision that shook the Milky Way and helped to build the thick disk we see today. Without Gaia's ability to measure motion so precisely, these stars would have remained lost. They would have remained lost in the crowd. Counting stars can reveal nearby companions if they are dense enough. Companions like the Fornax or sculptor dwarfs. But most of the Milky Way's merges left only scattered trails of stars. These trails are thin and faint, blending into the broader halo. The motions, however, do not blend so easily. A star that belonged to a captured galaxy keeps its orbital fingerprint. It keeps it long after the galaxy itself is gone. Gaia allows astronomers to read those fingerprints. By mapping not just where the stars are, but how they are moving, it becomes possible. It becomes possible to group them into families. Some of the families trace out streams. Others reveal entire past galaxies that merged and dissolved, leaving only their stars behind. Another key finding from Gaia is the Helmi streams. They were named after the astronomer Amina Helmi, who first identified them. These are groups of stars moving together through the halo. They are bound not by gravity anymore, but by a shared history. Their orbits and compositions point to a single dwarf galaxy consumed long ago, consumed 6 to 8 billion years ago. Again, the discovery was possible because Gaia provided the velocity data that separated these stars from the surrounding field. In a normal star map, they were invisible. In Gaia's motion data, they stood out like arrows pointing in the same direction. Gaia has also uncovered substructures within the disk itself, waves that ripple it, bending it like a warped vinyl record. Some stars are kicked into vertical motions, bobbing above and below the galactic plane. These distortions may be the scars of past encounters, perhaps with the Sagittarius dwarf galaxy or other satellites that pass through. They suggest that even today the Milky Way is still reshaping itself. It is reshaping under the influence of its smaller companions. The disk is not a settled structure. It is a dynamic living system that is shaped by its history. Traditional methods of discovery relied on identifying clusters of stars in the sky. This led to the catalogue of known dwarfs orbiting the Milky Way. But Gaia has shown that some overdensities are not galaxies at all. They are the shredded remains of once larger systems. Others that seem to be part of the halo are actually bound groups, faint dwarfs hiding in plain sight. The motion data provides the ability to disentangle these overlapping populations. It is like switching from a still photograph to a video where movement suddenly clarifies which stars belong together and which do not. The chemical analysis of stars tells astronomers about their birth environments. Stars formed in large galaxies tend to have higher metallicities, higher than those born in smaller ones. The motion tells them about the orbits. Combined, these datasets allow a reconstruction of when mergers happened. For example, the stars from Gaia Enceladus suggest a merger about 10 billion years ago. Other streams point to smaller events more recently. Piece by piece, Gaia is helping to build a chronology of the Milky Way's past. It is turning what was once speculation into something close to a family tree of mergers. The distribution of stellar motions also provides indirect evidence for something important: the shape of the Milky Way's dark matter halo. If stars from a past merger move in ways that do not match visible matter, it suggests that an unseen mass is shaping their orbits. By studying the motions of stars in streams and remnants, astronomers can probe the halo of dark matter that is surrounding our galaxy. The scope of Gaia's work is still expanding. Each new data release adds millions more stars, a finer precision and a greater depth. Already, astronomers have used Gaia to identify multiple possible past mergers, each with its own distinct stellar population. Some have evocative names: the Sequoia, the Thamnos, the Arjuna. Each one represents another galaxy that was lost to time. The faint dwarfs we see today, like Sculptor or Fornax, are just the survivors. Many others came before, leaving behind only streams, ripples, and odd motions. With Gaia, astronomers are no longer limited to the survivors. They can uncover the lost, the hidden, the galaxies that were long since consumed. It is galactic archaeology in the truest sense, the cusps and the dwarf galaxy problem. In the study of galaxies, and especially of dwarf galaxies, one of the persistent puzzles has been the way dark matter seems to arrange itself. The theory and simulation tell us one story, but the observations of the faintest galaxies often tell another. This gap between expectation and reality has become known as the cusp core problem. Dark matter seems to be spread out more smoothly than the theory suggests. It creates shallow central regions or cores rather than the steep, spiky cusps predicted. These predictions come from computer models. The origin of this problem lies in the earliest cosmological simulations from the late 20th century. When researchers began to model the universe's growth, they found something: growth under the influence of cold, dark matter. They found that small clumps of this mysterious substance tended to form halos with sharp, concentrated centers. In these halos, density increased rapidly toward the middle. This means that the closer one approached the center, the more extreme the gravity became. These steep centers were given the term cusps, and they became a hallmark of cold, dark matter theory. As computing power improved, more refined simulations were carried out, and again the cuspy centers emerged as the default outcome. This suggested that cusps were not simply artifacts of the earliest models. They were rather the natural results of how dark matter should behave under gravity. However, when astronomers turned to dwarf galaxies to test these predictions, the evidence changed. The evidence was not so clear. The motions of stars within many dwarfs pointed to a much flatter distribution of dark matter, a distribution near their centers. Instead of a density spiking as one approached the middle, it leveled off, forming a core. The simplest way to picture this difference is to imagine a hill versus a plateau. A cusp is like a steep hill rising sharply from the ground. A core is more like a flat plateau that remains level before dropping off. In terms of dark matter, a cusp means mass density becomes more extreme near the center. A core means that the density stays relatively constant across a wider region. In larger galaxies like the Milky Way, many things complicate the measurement. The stars, gas, and black holes, but in dwarfs where visible material is sparse, the gravitational fingerprint is clearer, the fingerprint of dark matter. The results collected across numerous systems point again and again to the presence of cores rather than cusps. Why is this a problem? Because if dark matter behaves as the simplest version of the theory suggests, cold, collisionless particles interacting only through gravity, then cusps should form naturally. Their absence means either the theory is incomplete or something has happened. Something has happened inside these galaxies to erase the cusps and create the cores. Researchers have approached this puzzle from both angles. On the astrophysical side, one explanation involves the role of stars and supernovae. Though dwarfs are faint and contain relatively few stars, they can still experience bursts of star formation that transform their structure. When massive stars die in violent explosions, they pump energy into the surrounding gas. They push it outward. This process, repeated many times over the lifetime of a dwarf galaxy, can stir the potential well. It can cause dark matter to redistribute. In essence, the repeated supernova-driven heating may puff up the inner dark matter. It may flatten the cusps into cores. This idea has gained traction in recent years. Simulations that include not only dark matter, but also baryonic physics, sometimes produce cores. These simulations include stars, gas, and feedback. They produce core-like distributions more in line with observations. It suggests that what appears to be a failure of dark matter theory might instead be an incomplete picture of how galaxies evolve. Without accounting for the messy processes of star formation, the simple dark matter-only simulations may misrepresent what actually occurs inside dwarfs. Yet not everyone is convinced that this solves the problem. Some dwarfs show signs of having very little recent star formation, yet they still appear to contain cores. Others suggest that the degree of feedback required to erase cusps might be too extreme. This is given the small number of stars that are present. In such cases, astrophysical explanations may not be enough. This forces researchers to consider whether dark matter itself behaves differently than the cold, collisionless picture. This leads to more exotic possibilities. One proposal is that dark matter might be self-interacting. This means that dark matter particles occasionally collide with one another. Unlike normal matter, which collides and radiates energy easily, dark matter is thought to be nearly invisible in its interactions. But if it does interact slightly, then over long timescales, those collisions could do something. They could naturally redistribute the particles inside galaxies, smoothing out the cusps, smoothing them into cores. Self-interacting dark matter has become one of the leading alternatives to the cold dark matter model, precisely because it can help solve the cusp-core issue. Other theories suggest that dark matter may not be made of heavy cold particles. Instead, it could consist of lighter, wave-like particles that naturally spread out. They resist the formation of sharp cusps. Ideas like fuzzy dark matter, where ultralight particles create a quantum pressure, to provide another potential path to explaining the cause. This pressure softens the central densities. These alternative dark matter models are attractive. They can explain dwarf galaxy observations without requiring as much reliance on complex feedback. However, they come with their own challenges. For example, if dark matter were too fuzzy or too strongly self-interacting, it could alter the structure of galaxies on larger scales. This would contradict other well-tested aspects of cosmology. Researchers must therefore balance these ideas carefully. They must seek models that fit the dwarf galaxies without breaking the successes of the theory elsewhere. Observationally, the cusp core debate continues to be tested with better data. Instruments that can track the motions of individual stars in faint dwarfs are critical. They allow astronomers to map the mass distributions more precisely. Surveys have provided the stellar velocities needed to construct detailed models of galactic structure. In parallel radio telescopes that measure the motion of gas in some dwarfs offer insights. They offer complementary insights. The problem remains stubborn because not all dwarfs tell the same story. Some of them appear to have clear cores, others seem to be more compatible with cusps. This variety raises the possibility that both outcomes may occur. This would depend on the specific history of each galaxy. A dwarf that experienced violent bursts of star formation might develop a core. A dwarf that evolved more quietly could retain a cusp. In this view, the cusp core problem is less about a universal mismatch. It is more about a spectrum of possibilities shaped by local conditions. The role of the dwarfs in building the Milky Way's halo, unlike the bright spiral arms or the dense central bulge of the Milky Way, the halo is diffuse and faint, stretching far beyond the visible disk. It is a sphere of scattered stars, globular clusters, and traces of past activity. The halo looks almost empty at a first glance, but it carries with it the history of the Milky Way's formation. Most scientists today believe that the outer halo was not built from inside the galaxy. Instead, it was built from the remains of many smaller galaxies. The idea that the halo is a graveyard of galaxies goes back to the late 20th century. Even then, researchers noticed that the stars in the halo were different from stars in the disk. Halo stars tend to be old with low metallicities. The disk is full of younger, more metal-rich stars. It is constantly refreshed by cycles of starbirth and supernova explosions. But the halo appeared to be frozen in time. The dwarf galaxies offered a natural explanation. These small systems have limited star formation. They often run out of gas early and never build up large amounts of heavy elements. If a galaxy like the Milky Way tore them apart and scattered their stars, the remnants would look very much like what we now observe in the halo. As sky surveys expanded, astronomers began to spot real evidence of past merges. Streams of stars, tidal tails, and clumps of unusual stellar populations all pointed toward one thing. They pointed toward dwarf galaxies being digested by the Milky Way. Over time, these features spread out and blurred. Eventually, they blended into the background of the halo. The process is so slow that even after billions of years, the marks are not fully erased. By carefully mapping the sky and measuring star motions, researchers can still pick out the past. They can see where one galaxy once ended and another began. The halo then can be thought of as a quilt stitched together from many smaller galaxies. Each dwarf that fell into the Milky Way left behind not only its stars, it also left its dark matter, its globular clusters, and its chemical fingerprints. When astronomers look at halo stars with spectrographs, they sometimes find unusual element ratios. These ratios don't match typical Milky Way stars. These chemical oddities act like passports. They prove that the star came from another system. By gathering enough of these signatures, scientists can reconstruct the history of how many dwarfs were absorbed and when. It is now widely accepted that the Milky Way's halo was built in two phases. The inner halo, which is closer to the galactic center, seems to contain certain stars that may have formed inside the Milky Way, or came from one or two massive merges. The outer halo appears much more chaotic. It stretches hundreds of thousands of light years into space. Its stars are arriving from a variety of smaller dwarfs. The distinction between the inner and outer halo has become clearer with data from Gaia. One of the most famous examples is the Gaia-Enceladus merger. It is sometimes called the Gaia sausage because of the shape it produced in velocity space. Another massive contributor was the Sagittarius dwarf, but these are not unique. Dozens of smaller dwarfs have likely disappeared entirely. They have left only their stars scattered across the halo. Many of these merges happened so long ago that the streams have fully dissolved. When we look at the outer halo today, the distribution of stars is patchy and irregular. Computer simulations confirm this picture. Large galaxies grow by accreting smaller ones, and their halos serve as the long-lasting record of that growth. Many globular clusters orbiting in the outer halo have suggestive chemical properties. They suggest the clusters did not form inside the Milky Way. Instead, they likely originated in dwarfs that were later destroyed. These clusters survived the fall, remaining intact while their parents were shredded. By studying which clusters share chemical or orbital features, astronomers can group them. They can group them into families. The dark matter halos of the dwarfs are harder to trace directly. But simulations predict that dark matter from cannibalized dwarfs is now mixed into the Milky Way's own dark matter halo. If this is true, then even the invisible skeleton of the galaxy was shaped. It was shaped by the slow reign of dwarfs over billions of years. The Milky Way is still accreting new material. It is still tugging at nearby dwarfs. Future astronomers will see their stars join the halo. Their unique fingerprints will be recorded in the chemical and kinematic fabric of the galaxy. The large galaxies are mosaics built from countless smaller units. The Milky Way's halo is the clearest reminder of this. It is a diffuse archive of stars that once belonged to dozens of independent galaxies. The chemical fingerprints of the dwarf galaxies. The stars in dwarf galaxies often show unusual element ratios. These ratios are unusual compared to stars in the Milky Way. One of the most striking patterns concerns the balance between two things, what astronomers call alpha elements like magnesium, calcium, and silicon, and iron. In the Milky Way, older stars show high ratios of these alpha elements to iron. This reflects enrichment by massive stars that exploded as supernovae early in history. As time went on, smaller stars also contributed iron through a different kind of explosion. This was the type Ia supernovae, and the balance shifted. In dwarf galaxies, however, this shift often appears at a much lower overall metallicity, lower than in the Milky Way. This suggests that dwarf galaxies had slower, less efficient star formation, so the influence of type Ia supernovae became important earlier in their chemical history. This means that stars in dwarf galaxies preserve a record of a very different pace of evolution. By comparing chemical fingerprints, astronomers can tell which Milky Way stars might have an origin in a smaller system that was later absorbed. Another clue comes from elements heavier than iron. These are formed in rare processes involving neutron capture. There are two main channels, the slow process or S process and the rapid process or the R process. The S process builds up elements inside aging giant stars. The R process happens in extreme events like neutron star mergers or certain supernovae. The dwarf galaxies often show unusual patterns in these heavy elements. Some of them are deficient in them. This reflects the fact that few such rare events ever occurred in their small populations. Others, however, show sudden bursts of R process enrichment. This is likely from a single dramatic event that seeded the entire galaxy with heavy elements. The ultra-faint dwarf Reticulum 2, for example, contains stars with enormous amounts of R process elements. This suggests that a single neutron star merger early in its history was enough to leave a chemical signature across the entire system. This kind of finding tells us that even in the smallest, faintest galaxies, The fingerprints of individual cosmic events can dominate the chemical record. In the Milky Way, such signals are washed out by billions of stars mixing over billions of years, but in the dwarfs they remain crisp and clear. This makes the dwarfs precious for testing theories of nucleosynthesis. This is the creation of elements inside stars and stellar explosions. There are also stars in the dwarfs that seem to be among the most primitive known anywhere. Studying their chemical fingerprints allows astronomers to peer back toward the earliest times, the cosmic times when the very first supernovae seeded the universe with elements beyond hydrogen and helium. Such stars carry direct evidence of processes that occurred more than 13 billion years ago. A fascinating detail is how chemical enrichment ties into star formation efficiency. In the Milky Way, the sheer mass of the galaxy helps to trap gas, recycle it, and create stars. In the dwarfs, by contrast, even a modest burst of star formation can blow out much of the gas. This can halt star formation for hundreds of millions of years. During that time, no new stars form to lock away the chemical signals. When the gas eventually cools and stars start to form again, the chemical fingerprint has shifted. This is because of enrichment from past supernovae. This stop-and-go process produces unique patterns in the ratios of elements. Another angle concerns the use of chemical tagging. This is the idea that groups of stars born from the same cloud share the same chemical fingerprint. In large galaxies, this can be very hard to apply because so many stars overlap. They overlap in chemical space. But in dwarf galaxies, the small populations make it easier to identify families of stars, families with common origins. This has led to insights about how these galaxies grew, and whether they experienced one major burst of star formation or several smaller ones, and how external factors like interactions with the Milky Way may have altered their histories. The ongoing work of spectroscopic projects like Apogee and DESI is making this picture sharper. By gathering chemical fingerprints for millions of stars, astronomers are doing more than cataloguing. They are not only cataloguing what exists today, but also tracing the family tree of galaxies. The dwarf galaxies, with their unusual and sometimes extreme element ratios, are proving to be key. The key to unlocking how galaxies formed, how elements were forged, and how the universe itself built up, how it built up the diversity of matter we see today. The satellites we haven't found yet. The Milky Way is almost certainly surrounded by a swarm of invisible companions, companions that are waiting to be uncovered. Identifying them is a task that requires not just better telescopes, but also clever analysis. It involves sifting through data, separating real patterns from random noise, and recognizing when a loose clump of faint stars is actually a galaxy in its own right. What makes this hunt exciting is that every new dwarf found reshapes our understanding of how the Milky Way came to be. Each discovery helps to test theories of galaxy formation, star formation, and dark matter. If the predictions are correct, then the majority of our galaxy's satellites remain hidden. The newer generation of surveys will be crucial, especially those that cover wide patches of the sky in exquisite detail. Astronomers are especially eager for the Vera C. Rubin Observatory. It is just about to begin full operations in late 2025. Its wide and repeated scans of the sky should pick out faint dwarfs that were previously overlooked. It will fill in the map of our galactic neighborhood with more companions. Some dwarfs may also be hidden because they are located in tricky places. If a small galaxy lies behind the bright band of the Milky Way's disk, its light can be drowned out by the sheer density of stars and clouds in our line of sight. The glare of starlight and dust makes it extremely difficult to separate a satellite, to separate it from the background. This means that many of the missing dwarfs might actually be lurking. lurking right in the direction we tend to avoid in sky surveys. Finding them requires new ways of peering through dust and starlight, such as using infrared light, which can cut through cosmic haze more effectively than visible light. There's also the possibility that some unseen dwarfs are not just faint, but almost entirely dark. In other words, they may be galaxies where dark matter dominates almost completely, with hardly any stars lighting them up. If such objects exist, they would be nearly impossible to find directly. They would only reveal themselves through their gravitational effects, perhaps by the way they tug on stellar streams in the Milky Way's halo, or distort the motion of gas in the outskirts of our galaxy. Already astronomers have been surprised by dwarfs discovered in the last 2 decades. Some of them are astonishingly faint, like Segway 1. It has fewer stars than a typical star cluster, but a mass dominated by dark matter. Others, like Crater 2, are enormous in size but diffuse. They spread their stars over a wide area with barely any central brightness. These finds suggest that instead of neat compact dwarfs, the unseen satellites might come in a variety of shapes and structures. This forces scientists to expand their definitions. Beyond the Milky Way, the search extends to our nearest big neighbor, the Andromeda Galaxy. Andromeda already has a rich system of satellites, some of which are surprisingly aligned in thin planes, raising questions about how they formed. Yet here, too many satellites are predicted but not yet observed. The same applies to other nearby galaxies, such as the Triangulum Galaxy. If the missing satellites problem exists everywhere, then it's not just about our Milky Way. It's a deeper issue tied to the way small galaxies form across the universe. A century ago, astronomers didn't even know about dwarf galaxies. It wasn't until surveys deepened and methods improved that these small companions began to show up. Each generation of tools reveals more faint and elusive systems. This suggests that our picture is always incomplete. The satellites we haven't found yet may simply be waiting for the next leap in observation. In that sense, the story of the missing dwarfs is about the limits of our instruments, as much as it is about the galaxies themselves. If more ultra-faint dwarfs are found, it would bring observed numbers closer to predictions. This would help to bridge the missing satellites problem. If, on the other hand, new discoveries continue to fall short of expectations, it would point to something deeper being wrong in our models. Either outcome would be significant. Some of the unseen dwarfs may already be gone. They may have been completely destroyed by the Milky Way. Their stars might now be scattered in streams across the halo. Their dark matter halos merged into the larger structure of our galaxy. If this is the case, then the missing companions are not truly missing. They are ghosts, their remnants spread out across the sky, stripped to the bone. How the satellites lose their gas. Gas is the raw fuel for star formation, and without it, a galaxy becomes quiet. It fades into a system where stars only age and die, with little chance of new ones being born. Many of the dwarf galaxies that sit close to our own galaxy are almost entirely devoid of gas. They look barren compared to what we think of as a normal galaxy. This strange emptiness has a story behind it. A story that involves not just gravity, but also the physics of how gas behaves in space, and the violent forces that are at play when galaxies interact. One of the main ways a dwarf galaxy loses its gas is through a process called ram pressure stripping. To imagine this picture, a car moving quickly down a highway with the windows open. The air pushes hard against anything loose inside, trying to blow it out of the car. Now replace the car with a small galaxy, and replace the rushing air with the hot, thin plasma that fills the space between galaxies. This is called the intracluster, or circumgalactic medium. As the dwarf galaxy speeds through this medium, the gas inside it feels the push, and if the pressure is strong enough, the gas is blown out into space. This can happen dramatically when a satellite plunges through the halo of gas surrounding a galaxy. a massive galaxy like the Milky Way. The stars, which are much heavier and less affected by this drag, remain behind, but the gas, the lifeblood of the galaxy, is stripped away. This explains why many dwarf spheroidal galaxies are so gas-poor. These are the common satellites in our local group. They orbit close to the Milky Way and have been exposed to strong stripping effects for billions of years. Some of them may have once looked more like the LMC, but after multiple passes through the Milky Way's halo, they were stripped down to their bare bones. Today, they shine faintly with ancient stars, while their gas, once dense and bright, has long since been blown into the Milky Way's environment. But ram pressure is only one piece of the story. Another major process is tidal stripping, which is caused by gravity itself. When a smaller galaxy orbits a larger one, the difference in gravitational pull creates stresses, powerful stresses. These stresses can tear away stars. Gas is even more vulnerable to this process because it can be pulled away more easily. In some cases, the stars in the center remain intact, while both the gas and the outer stars are peeled away. What is left behind is often a smaller, fainter version of the galaxy. It orbits like a remnant of its former self. There is also the role of the galaxy's own stars. Star formation itself is a violent process. When a new generation of massive stars forms, many of them quickly explode. They release tremendous amounts of energy. In a large galaxy, the gravity is strong enough to keep most of this material bound. But in a dwarf galaxy, the gravitational pull is weaker. The shock waves and winds from supernovae can push gas outward. And once it is far enough from the center, other processes can finish the job. Processes like ram pressure or tidal stripping, they can carry it away permanently. This self-driven loss makes it even harder for dwarfs to hold on to their material. One dramatic example of stripping is seen in jellyfish galaxies. These are not dwarfs, but larger galaxies that show long trailing tentacles of gas, tentacles streaming away as they move through clusters. The same physics applies to dwarfs, only on a smaller scale. If a dwarf plunges too close to the hot gas halo of a massive galaxy or cluster, it can leave behind long, thin trails of stripped gas. Sometimes they glow faintly as stars form inside them. These trails are the last sign of the galaxy's lost potential. They show where its star-forming material was stolen away. In the local group, astronomers can directly see the differences between dwarfs that have been stripped and those that have not. Satellites like Sculptor Draco or Ursa Minor orbit closer to the Milky Way. They have been stripped again and again until little more than their stellar skeletons remain. Gas-rich dwarfs arriving from the outskirts are slowly transformed into barren systems. This happens as they are drawn deeper into the halo. Interestingly, Andromeda's halo of hot gas may be even more extended and massive, more massive than that of the Milky Way, making its stripping effect stronger. Observations of faint stellar streams around Andromeda also show that stripping is not just about gas. It is actively dismantling the galaxies themselves, scattering their stars, scattering them into Andromeda's outer halo. Over time, these processes combine to produce a kind of natural selection. The dwarfs that fall into a giant galaxy's orbit are gradually robbed of their ability to make new stars. Some of them may survive as faint satellites, their structure preserved but their future cut off. Others may be shredded entirely, their stars forming streams that blend into the halo of the larger galaxy. In every case, the stripping reshapes both the small galaxy and the giant it orbits. The stripped gas can fall onto the host, fueling new star formation. The stripped stars help to build its halo. The fate of a dwarf galaxy then depends on where it orbits and how fast it moves, and how much gas it started with. A dwarf that remains far from the host may keep its gas for billions of years. It may continue to form stars. A dwarf that plunges deep inside the halo may lose everything in just a few close passes. Some of them may even be reduced to ultra-faint galaxies. These faint remnants show us the end state of the stripping process. The satellites beyond the satellites, the sub-galaxies. If the Milky Way has satellites, could those satellites themselves have satellites? Could the cosmic hierarchy extend one more step down? Could it form what might be called sub-galaxies? Is there a natural limit to how far down the ladder one can go? When astronomers run large simulations of the universe, they feed in the basic ingredients: dark matter, gas, radiation, and the physics that governs their behavior. Out of those simulations comes the cosmic web, with filaments and nodes where galaxies form. Zooming in closer, one finds the halos of dark matter that should host galaxies, and within those halos, smaller halos that should host smaller galaxies. Theoretically, there is nothing to stop the process from continuing further, with halos inside halos inside halos, much like Russian nesting dolls. If this picture is correct, then a dwarf galaxy should itself have tiny companions. A galaxy like Fornax or Sculptor, faint little galaxies clinging to it, orbiting their larger but still modest parent. The difficulty is that such systems would be extremely hard to find. The Milky Way's own dwarfs are already faint and elusive. They were discovered only with careful surveys and deep imaging. A sub-satellite galaxy would likely be even dimmer, its stars so few that only the nearest examples might ever be visible. The dark matter halos predicted to host them could exist without producing much starlight at all. This would make them effectively invisible. Still, if even one such system could be found, it would be a strong confirmation. A confirmation that the hierarchical picture of structure formation is right down to the smallest scales. The hints that such systems might exist come from looking closely at the more massive dwarfs. Take the LMC and the SMC. They are relatively large as dwarfs go, and both show signs of having interacted with smaller companions. A few tiny faint objects discovered in their vicinity could be satellites of the clouds. Satellites of the clouds rather than of the Milky Way itself. If this is confirmed, that would mean we already have evidence for sub-galaxies right on our cosmic doorstep. It also raises the intriguing possibility of the origin of stripped material. Some of the stars and gas being stripped from the Magellanic Clouds into tidal streams might have originated from smaller companions caught in their gravitational pull. But what about the smaller dwarfs? Could a faint spheroidal galaxy like Draco truly have its own even tinier companions? Draco itself is barely clinging to survival in the Milky Way's tidal field. Here, the answer is less clear. Theoretically, dark matter models suggest that every halo, no matter how small, has substructure. But the shallower the potential well of the main dwarf, the less likely it is to hold on. To hold on to such companions in the face of the Milky Way's overwhelming gravity, any subgalaxy would need to be extremely close to its parent to avoid being torn away. It would orbit more like a satellite moon than a far-flung companion. It would be huddled tightly to the core. Their faint starlight would blur into the background of their parent stars. This would make them nearly indistinguishable. The ultra-faint companions of ultrafaints would be systems with only a few hundred stars. They would be bound together more by their shared dark matter halo than by gravity between stars. To detect them, one would likely need not just imaging but also measurements of stellar motions, looking for groups of stars that move together as if they belong to a hidden structure. In principle, similar data to Gaia could one day reveal something. Whether dwarfs like Fornax have tiny clumps of stars moving in ways that betray a connection, a deeper connection. If sub-galaxies exist, do they form stars the same way as larger galaxies? Or are they so faint and fragile that their gas gets stripped away almost instantly? Perhaps many of them are dark, miniature halos with little or no star. formation, invisible to us except through gravitational effects. In that case, they might still be detected indirectly by their influence on the dynamics of stars in their parent dwarf, or by the way they create subtle distortions in tidal streams. Centuries ago, scientists wondered if the solar system could have smaller systems within systems, planets with moons, moons with even smaller moons. In time, we discovered that yes, some moons do have companions, though usually they are small captured objects rather than stable long-term systems. The same question now arises on the galactic level. How far down does the nesting go? Does the cosmic hierarchy stop at the dwarfs, or does it keep on going one more step? If sub-galaxies are confirmed, they would change how we think about the Milky Way's family tree. No longer would it be a simple story of large galaxies surrounded by small ones. Instead, the picture would become more complex with a branching structure, a structure where even modest dwarfs carry their own miniature entourages. This would make galactic archaeology richer but also harder. One would need to untangle not just the history of the Milky Way consuming dwarfs, but also of dwarfs consuming their own satellites before being consumed themselves. The chemical signatures of stars, the patterns of stellar streams, the shapes of tidal debris, all would need to be reinterpreted with this added layer of complexity. Speculative though it is, the notion of sub-galaxies fits naturally into a broader theme, the theme of the universe as a structure built from hierarchies. Galaxies form within dark matter halos, which themselves sit within larger halos, and so on scales both vast and minute. Gravity seems to favor the building of nested systems. Whether there is a limit, whether the ladder of satellites stops here or goes one step further, remains a question that could, in principle, be answered in the next few decades. This will happen as our ability to trace faint structures and subtle motions extends. Comparing the Milky Way and the Andromeda's satellite systems. In our local group, the Milky Way and Andromeda seem like twin giants, giants ruling their own territories. Both of them are spiral galaxies. Both of them are surrounded by swarms of dwarf companions, and both of them are slowly moving toward a cosmic collision billions of years in the future. Yet when scientists begin to compare their satellite systems in detail, the picture changes. The picture becomes less balanced. Andromeda seems to have more satellites, different kinds of satellites, and in some ways a richer set of examples that challenge what we think a galaxy family should be. This head-to-head comparison of the two systems is great for testing ideas about galaxy formation, cosmic environment, and the role of dark matter, the role in shaping small-scale structures. One of the clearest differences lies simply in the numbers. The Milky Way has at last reliable count about 60 known dwarf satellites, though new discoveries continue to add to that list. Many of these are ultra-faint galaxies which are hard to see even with modern surveys. Andromeda, however, boasts a larger population with at least 90 confirmed satellites, possibly more depending on how deep the observations go. Some of this difference comes down to a vantage point. We live inside the Milky Way, so the faint dwarfs near our disk are often hidden behind dense fields of obstructions. Observing Andromeda, by contrast, means looking at its system from the outside. This makes its satellites easier to map. Still, even after accounting for biases, Andromeda seems to have genuinely more companions. Did Andromeda simply form in a way that favored capturing or retaining more dwarfs, or has the Milky Way lost some of its former satellites over time through tidal stripping and through past merges? Beyond the raw numbers, the mix of satellite types also differs. The Milky Way's satellite system is dominated by ultra-faint dwarfs, and a handful of brighter examples. Most of the Milky Way's satellites, like Draco or Ursa Minor, are gas-poor spheroidals. They have little or no current star formation. Andromeda, however, has several bright satellites of its own, including M32 and M110. both of which have histories that seem more violent. M32, for instance, may be the stripped-down remnant of a once larger galaxy. Its outer layers were torn away by Andromeda's gravity. M110 shows evidence of past star formation episodes. These episodes suggest bursts triggered by tidal interactions. Even the smaller Andromeda dwarfs show different chemical fingerprints. These are different compared to the Milky Way's companions. This hints at different paths of enrichment and star formation over time. Several studies have suggested that a large fraction of Andromeda's satellites lie in a plane, a giant thin plane almost like a cosmic disk of dwarfs orbiting together. This is not what theory predicts. Dark matter simulations tend to produce satellites that are distributed in more spherical halos, not neatly arranged planes. Some scientists argue that the pattern may be partly coincidental, but the alignment is too strong to dismiss entirely. By contrast, the Milky Way's satellites are somewhat more scattered, though even here hints of planar alignments have been suggested. If Andromeda's plane is real, it may mean that groups of satellites fell in together. They fell in as coherent associations rather than arriving one by one. Many of the Milky Way's dwarfs appear to have shut down their star formation long ago. They have turned into fossil systems. In Andromeda, some of its satellites show evidence of more extended histories. Star formation is lasting longer or restarting after initial pauses. This suggests that Andromeda may have influenced its companions differently, perhaps because its gravitational tides or past merges created more complex interactions. Understanding why Andromeda's dwarfs are more chemically diverse and historically active could help. It could help explain why two seemingly similar host galaxies ended up with such different families. There is also the matter of a satellite's brightness and detectability. The Milky Way's ultra-faint dwarfs are so dim that some contain only a few thousand stars. Andromeda surely has equivalents, but at its greater distance they are extremely hard to spot. Its distance is about 2.5 million light-years. Current surveys are just barely reaching the limit where such systems could be identified. Improved instruments may eventually bring its faint end into closer alignment with the Milky Way's. But if it doesn't, and if Andromeda truly lacks the same abundance of ultra-faints, then the difference may point to deeper physical causes. Causes such as variations in how dark matter subhalos light up with stars in different environments. The Milky Way's Magellanic Clouds are unique. They are massive enough to have their own satellite candidates. Their ongoing interaction with the Milky Way is creating the Magellanic Stream. Andromeda does not seem to have direct equivalents of this kind of paired gas-rich companion, though some argue that M32's history as a stripped galaxy represents a parallel case, a case of a massive neighbor, reshaped by tidal forces. The fact that the Milky Way has its own special configuration highlights something. With two bright irregulars that are still very much alive and forming stars, it highlights how each host galaxy builds a unique environment for its satellites. From a theoretical perspective, the Milky Way-Andromeda comparison is invaluable. By examining two spiral giants of similar mass and age, but with different satellite systems, astronomers can test whether discrepancies are due to observation, environment, or physics. If satellite alignments like Andromeda's turn out to be common, our models will need to adapt. If the Milky Way's satellites are unusually quenched and faint, that may point to something peculiar about our galaxy's halo environment. Each difference becomes a test case, a way of probing the limits of our models. In many ways, the Milky Way and Andromeda resemble siblings. They have similar backgrounds but distinct personalities. Their differences remind us that even two neighbors in the same cosmic group can take separate paths. Paths shaped by the accidents of merges, tides, and the local environment. By continuing to compare them, astronomers hope to understand each system more clearly, and they hope to uncover the general rules that govern galaxy formation throughout the universe. The local group as a test bed. The local group is neither a crowded cluster where galaxies crash together too often, nor is it too empty, where interactions might be too rare to notice. Instead, it is a loose assembly of three large galaxies: the Milky Way Andromeda and the smaller but still significant Triangulum. They are surrounded by more than 80 dwarf galaxies of varying shapes, sizes, and brightness. This mix of giants and minnows creates a miniature version of the broader universe. It is scaled down to a distance range we can actually resolve with telescopes. For astronomers, the local group is something like a test field. By comparing how dwarfs orbit the Milky Way with those around Andromeda, and then looking at how Triangulum interacts with both, they can build a richer picture of the forces that govern galaxy formation. The individual dwarfs represent snapshots of different evolutionary stages. Each system carries its own imprint of past mergers, chemical histories, and environmental effects. The local group makes these comparisons possible in a way that studying distant clusters cannot. Triangulum is often overshadowed by its larger neighbors, but it plays an important role in this laboratory setting. As the third major spiral galaxy in the local group, it is smaller than the Milky Way or Andromeda, but it is large enough to host its own system of dwarfs. These companions are harder to study because Triangulum is farther away, but they provide a critical third point of comparison. If Andromeda's satellites look different from the Milky Way's, Triangulum helps to decide whether that difference is unique to Andromeda or a broader pattern. For example, if both Andromeda and Triangulum show more satellites with elongated structures, while the Milky Ways are more compact, that suggests something about environment and history, not about chance. The local group also offers a chance to study how dwarfs interact, not only with their giant hosts but also with each other. In some cases, small galaxies orbiting near each other may form temporary pairs, their mutual gravity tugging at their stars even before the larger galaxy's pull takes over. There is evidence that some of the Milky Way's companions once entered together. They came in as small groups already linked by gravity before falling into our galaxy's halo. The same may be true for Andromeda. These associations of dwarfs are like smaller versions of the local group. They show how cosmic structure builds up from the bottom. By mapping out their positions and motions, astronomers can begin to reconstruct their history. Which dwarfs came in as individuals and which arrived as part of larger infalls. Some of the local group's dwarfs show extremely primitive chemistry. Others reveal a richer history. By comparing these patterns across the dwarfs tied to the Milky Way, Andromeda, and Triangulum, astronomers can test whether giants shape their satellites' chemical lives, or whether dwarfs largely set their own pace before being captured. Dark matter study too benefits from the local group's arrangement. Because we can measure the motions of stars in nearby dwarfs with great precision, the local group's dwarfs provide strong tests of how dark matter is distributed on small scales. And, by having three main host galaxies, each with their own satellite system, researchers can ask whether the cusp versus cause problem shows up everywhere, or only in specific environments. The Milky Way and Andromeda are on a course to collide, and Triangulum may be drawn into that drama as well. Their dwarfs will be caught up in the process, stripped, merged, or scattered. Some of the faintest satellites could dissolve entirely, their stars adding to the smooth halos of the giants. Others may survive, but be flung into new orbits. The local group offers not only a snapshot of current conditions, but a preview of future galaxy evolution on a small scale. Studying it now allows astronomers to anticipate the fates of larger systems elsewhere. For many dwarfs within the local group, astronomers can resolve individual stars, not just the blended light. That means they can measure distances more accurately. They can identify variable stars that serve as cosmic yardsticks, and even trace star formation histories by counting stars of different ages. This level of precision is impossible for dwarfs in more distant groups. There they appear only as faint smudges. The local group thus provides a kind of ground truth, a truth against which models and theories can be tested before being applied farther away. The local group is small by cosmic standards, but in its modest boundaries it contains a universe of lessons. By looking at it as a whole rather than only at the Milky Way, astronomers can see the interplay of the three major galaxies and the dozens of dwarfs, each one adding a piece to the puzzle. The fate of the Magellanic Clouds in the Andromeda collision. Looking into the future of the Milky Way, one event dominates all predictions: the inevitable collision with the Andromeda Galaxy. This enormous encounter will slowly reshape the sky, mixing stars and blending gas clouds. But while the drama of the two giant spiral galaxies merging tends to capture the imagination, there are quieter but equally intriguing questions that arise. Questions when we think about the smaller players in this cosmic dance. Chief among them are the LMC and the SMC. What will become of them when their parent galaxy collides with Andromeda? As we discussed earlier, the LMC may be massive enough to tug at the Milky Way's halo. It may even shift the balance of our galaxy's motion. This means that when Andromeda enters the stage, the Magellanic Clouds will not be passive observers. They will not just be swept up by whatever happens. They will be dynamic participants, each one bringing their own gravitational influence and their gas clouds and their orbits into the larger collision. Their future is tied not just to the Milky Way, but also to the timing of when the galaxies meet. Simulations of the Milky Way-Andromeda collision suggest something. The first close approach between the two giants will happen about 4 billion years from now. A complete merger will follow a few billion years later. By that time, the LMC and the SMC may no longer look like the lively galaxies we know today. The tidal forces are already slowly pulling them apart, and the Milky Way's gravitational field is stripping their gas. Some models predict that within a few billion years, the Magellanic Stream will have emptied their fuel, most of their fuel for star formation. This will leave behind dimmer remnants of their once bright selves. If this is the case, they may enter the Andromeda merger as ghostly fading satellites, the shadows of their former vibrancy. But there is another possibility. Because the LMC in particular is so massive, it may not be destined to remain a satellite, not indefinitely. Its orbit is decaying, and many astronomers think that in about 2 to 3 billion years it could merge with us. Long before Andromeda even arrives, the LMC could merge directly with the Milky Way. If that happens, the story changes dramatically. Instead of being swept into the Andromeda collision as a separate companion, the LMC's stars and gas would already be blended into the Milky Way's disk and halo. In a sense, the Milky Way would enter its grand collision already swollen with fresh material from a smaller merger. The SMC, which is less massive, might follow the LMC into the Milky Way as well. It would get dragged along in its gravitational wake. If this sequence plays out, the Magellanic Clouds as distinct entities will not survive. They will not survive to witness the great Milky Way-Andromeda union. Yet, if the LMC and SMC manage to persist as separate galaxies until the collision begins, their orbits would be reshaped in dramatic ways. The combined gravitational pull of Andromeda and the Milky Way would likely fling them into new paths, tossing them into eccentric loops, or even ejecting them into intergalactic space. In some simulations of galaxy merges, satellites are not gently absorbed. They are hurled away at high speed, victims of the shifting balance of forces. It is not impossible that the Magellanic Clouds could end up exiled from both galaxies. They could drift into the wider local group as free-floating dwarfs, no longer bound to a single parent. Another possibility is that they might be captured by Andromeda rather than the Milky Way. When the two galaxies merge, their stars and gas are mixed in a chaotic process, but the satellites can sometimes switch allegiance. This depends on how the gravitational tides unfold. The LMC, for example, could end up orbiting the newly merged Milky Way galaxy, our future combined system of the Milky Way and Andromeda, but on a path more influenced by Andromeda's core stars than by our original structure. The clouds would then live on, but as absorbed fragments of a system much larger than anything they have known. Galaxy collisions are not like car crashes. The stars almost never physically hit each other because the spaces between them are so vast. Instead, what happens is a violent reorganization of orbits and gas. When large supplies of gas are funneled into the centers of galaxies during mergers, they can trigger starbursts. The LMC and the SMC are both rich in gas. If they still hold on to their gas when the merger occurs, they could act like reservoirs feeding the starbursts that will blaze during the collision. In this way, the Magellanic Clouds might fuel some of the most spectacular light shows of the future night sky. The LMC in particular seems to sit inside its own dark matter halo. This makes it sturdier against tidal destruction than other dwarfs. If this halo is as massive as some measurements suggest, it could give the LMC extra resilience during the merger. While many smaller satellites may be shredded into streams and faint debris, the LMC could remain a coherent structure for much longer. It could possibly survive as a distinct core within the merged Milky Way galaxy. If so, billions of years from now, astronomers living inside that distant future galaxy might still be able to trace a remnant of the Magellanic Clouds hidden within the grander system, like fossils embedded in rock. While we cannot yet say with certainty which destiny awaits them, the fact that they are large and active makes their role in the future cosmic story fascinating. Billions of years from now, when the Milky Way and Andromeda collide, the skies above Earth, if Earth is still here, will be filled with dazzling displays of starlight. Among the many stars swept into the new arrangements will be the stellar legacies. The stellar legacies of the LMC and the SMC. Can the dwarfs escape their masters? The relationship between a giant galaxy and its smaller satellites is often pictured as one-sided. The big galaxy pulling its companions inward, stripping them of stars and gas and absorbing them. But nature is rarely so simple. Gravity may be a dominant force, yet it is also dynamic. It changes in response to motion encounter and cosmic timing. This means that satellites are not always destined to fall. Some of them may gain enough speed to slip free of their host's pull. To understand how a dwarf galaxy might escape, one first has to consider escape velocity. Every massive object creates a kind of invisible boundary, a boundary defined by how much energy it takes to get away from it. For Earth, rockets must reach about 11 kilometers per second to escape the planet's gravity. For the Milky Way, the escape velocity near the Sun's location is around 550 kilometers per second. A dwarf galaxy bound in an orbit typically moves well below that speed. Yet, under certain circumstances, gravitational boosts can push it higher. The question becomes, where could that energy come from? One obvious source is an interaction with another galaxy. When two giants merge, their gravitational fields overlap and evolve in chaotic ways. The satellites caught in the crossfire may find themselves accelerated. This happens as the balance of forces shifts. Some of them will be pulled deeper into the centers of the new system. Others may be thrown outward. Computer simulations of such mergers have shown satellites being flung into intergalactic space. They are stripped away not by destruction but by velocity. They continue on as rogue dwarfs, no longer orbiting a larger master but drifting through the void. There is also the possibility of a slingshot effect, in a way similar to how spacecraft use planetary flybys to gain speed. Dwarfs can receive a gravitational assist when they pass near a massive companion. If the geometry is right, this can add to their orbital energy rather than subtract from it. Instead of spiraling inward, the dwarf picks up speed and shifts onto a wider path, a more eccentric path. In extremely rare cases, that path may lead to an escape. It is worth noting that this mechanism is not theoretical alone. Astronomers see the same effect when small galaxies pass near each other. One is tightening into the orbit of the giant, the other is being sent away at a higher velocity. Evidence for potential escapees has appeared in the study of high-velocity galaxies. In a few regions of the nearby universe, dwarfs have been detected moving at high speeds, speeds that are too high to remain comfortably bound to their supposed hosts. For example, in surveys around galaxy clusters, some dwarfs appear to be on certain paths that will eventually take them out of the cluster altogether. Clusters are extreme environments far denser than a single galactic halo, but they provide a useful analogy. If dwarfs can be ejected from clusters, they could also be ejected from individual galaxies. This could happen under the right conditions. For decades, astronomers debated whether the LMC and SMC were long-term satellites, or more recent arrivals passing through for the first time. Measurements of their proper motion with the Hubble Space Telescope suggested something. They are moving faster than expected for a deeply bound system. Some models propose that the clouds may eventually escape the Milky Way's grip. This depends on how their orbit evolves and how dynamical friction slows them down. If they do remain, they will likely merge with the Milky Way. If they do not, they could become wandering galaxies of their own. This would happen before eventually being captured by Andromeda or cast into open space. A dwarf's ability to escape is closely tied to how massive and extended the halo really is. If the Milky Way's halo is larger than expected, an escape becomes much harder. If it is smaller, more dwarfs could find their way out. The current models of the halo are still uncertain. This leaves the question of ejected dwarfs open. Even if the dwarf itself does not escape, parts of it can. Stellar streams can persist for billions of years. They wander through the halo and sometimes even leave it. In time, they may seed faint intergalactic structures, the remnants of galaxies that once orbited but then unraveled. In the early universe, when galaxies were smaller and more numerous, encounters were more common. The dwarfs may have been thrown around much more often. They may have been shuffled from one host to another or set free into the void. Some of today's isolated dwarfs might be the survivors of those ancient expulsions. They no longer carry the memory of their original masters, only their own faint light drifting far from the nearest giant. The possibility that these galaxies exist challenges astronomers to look for patterns. Are there too many lone dwarfs to explain by standard formation theories? Could a significant fraction of them be escapes rather than original independents? If dwarfs can escape the Milky Way or Andromeda, they do not necessarily vanish. They do not vanish from the cosmic stage. Instead, they may linger in the gravitational reach of the local group as a whole. In this sense, an escape is relative. A dwarf may leave the Milky Way's halo, but remain bound to the larger structure, a structure that includes Andromeda and Triangulum. Over billions of years, such dwarfs could be recaptured. They could join new hosts or remain as free-floating members of the local group's population. The future of dwarf galaxy studies with next-gen telescopes. In the coming decades, dwarf galaxies may move from the sidelines of astronomy to its very center. For much of the last century, they were treated as curiosities, too faint, too fragile to be more than supporting characters in the grand drama of cosmic structure. Yet again and again, they have proven to be key players. The challenge has always been finding them, but with the rise of next-generation telescopes, the shadows will be pulled back. Soon, astronomers expect to uncover not dozens, but perhaps thousands of new dwarfs. Each one will be a clue to the hidden history of the universe. The first revolution will come from the Vera C. Rubin Observatory. It was formerly called the LSST. This facility will map the entire visible southern sky in unprecedented depth. Unlike past surveys which targeted particular regions, the Rubin will sweep the whole panorama. It will do so again and again over a decade, producing a living movie of the cosmos. For dwarf galaxies, this is a goldmine. Many of the faintest dwarfs remain undiscovered, not because they are too far away, but because they blend into the background. Their stars are too few to stand out individually, and their overall brightness barely rises above the night sky. But when a survey like the Rubin's collects images over the years, the faint signal can be teased from the noise. The hope is that what now looks like empty space will suddenly be revealed to contain structures, countless hidden structures. Astronomers expect the Rubin to uncover the faintest known galaxies in the local group, perhaps approaching the very edge of what counts as a galaxy. The Rubin's census could tip the balance. If it finds them in large numbers, the current models stand. If not, the universe may be telling us something deeper. The Rubin will not work alone. Another major player will be NASA's Nancy Grace Roman Space Telescope. While the Rubin is a ground-based surveyor, the Roman will operate from space. It will provide sharper views that are unobstructed by the Earth's atmosphere. Its wide-field instrument is designed to image enormous swaths of the sky. It will do so at a Hubble-like resolution. This means the Roman will not only confirm dwarf candidates spotted by the Rubin, but also reveal detailed structures within them. The faint stellar streams, central clusters, or signs of recent interactions could all be traced. The Roman will also look farther afield beyond the local group. With its reach, astronomers expect to spot dwarfs orbiting galaxies tens of millions of light-years away. This allows us to see whether the patterns we observe locally hold across the wider universe. Together, the Rubin and the Roman will create something like a two-part system, one that is scanning the broad and deep from Earth, the other that is zooming in from space. Add to this the James Webb Space Telescope, which is already operational, and the picture becomes even richer. The Webb, though not designed as a survey telescope, can probe the inner lives of dwarfs. It does so with infrared sensitivity, peering through dust and catching the faint glow of ancient stars. Already the Webb has begun to uncover distant galaxies that are so small they resemble early dwarfs. They offer a glimpse of what the universe's first building blocks looked like. In the future, the Webb could be used to study nearby ultra-faint dwarfs in exquisite detail, especially their stellar populations. Beyond these flagship observatories, many other projects will contribute in vital ways. Radio arrays like the Square Kilometre Array will map hydrogen gas. They will reveal how much fuel for star formation the dwarfs still carry, and how that gas is stripped away by larger galaxies. The extremely large telescopes, or ELTs, on the ground with mirrors over 30 meters wide, will let astronomers resolve individual stars in distant dwarfs. They will turn smudges of light into detailed stellar systems. Even high-energy observatories may weigh in. They will study how supernovae and black holes within dwarfs influence their structure and survival. One of the most exciting possibilities is that the Rubin and Roman will find whole new classes of dwarfs that we did not know existed. There could be galaxies that are so diffuse their stars are spread over vast distances, looking like loose associations until careful surveys reveal their dark matter halos. There might be gas-rich dwarfs hidden behind dust, or relic galaxies that never grew beyond their original burst of star formation. Another area where next-gen telescopes will shine is in tracing the dynamics of dwarfs. By watching the stars move within them, astronomers can measure how much dark matter is present and how it is distributed. The same telescopes may also give us the first glimpses of star formation in tiny galaxies. The tiniest possible galaxies. Do ultra-faint dwarfs still form new stars today, or did they stop billions of years ago? If some of them remain active, they could challenge our ideas about how galaxies regulate themselves. If they are universally quiescent, that too would be revealing. It would show that there is a lower limit below which star formation cannot persist. Understanding this threshold will help to refine our models of how galaxies die. If dwarfs reionize the early universe, as many suspect, then mapping their modern descendants is like piecing together the family tree of the cosmos. Each faint smudge is a survivor, carrying the memory of an age when galaxies were newborn. By studying them in vast numbers, astronomers may reconstruct how the first light spread across the dark universe. The future is therefore one of abundance. Instead of struggling to scrape together a few faint dwarfs, scientists may soon have more than they can easily catalogue. The challenge will shift from discovery to interpretation. How to fit thousands of small galaxies into a coherent story of cosmic evolution. But that is a challenge astronomers are eager to face, because every faint galaxy carries with it a secret about where we came from and where we are going. Do the dwarf galaxies challenge our definition of life-friendly galaxies? When people imagine galaxies that might give rise to life, they tend to picture grand spirals or sprawling ellipticals with billions upon billions of stars. These giant structures feel like the natural candidates for hosting complex chemistry, and planets and perhaps even civilizations. Their vastness provides both diversity and stability. Countless stellar systems, some violent, others quiet, spread across a disk or spheroid, a place where gas and dust recycle endlessly. But the dwarf galaxies, with their fragile bodies and sparse populations, paint a different picture. They are stripped-down environments, often shaped by the whims of larger galaxies. They have fewer stars, less shielding against radiation, and more chaotic histories. And yet, could life emerge within such tiny and harsh settings? The first hurdle is simply the matter of numbers. A galaxy like the Milky Way might have several 100 billion stars. This gives it countless chances to form Earth-like planets in stable orbits. A dwarf galaxy might contain only a few million or even a few 100,000 stars. That means the odds of having multiple long-lived sun-like stars are dramatically reduced. The ultra-faint dwarfs often host nothing more than ancient, dim stars. With so few potential homes, the probability of life starting somewhere seems lower. But reduced chances are not the same as an impossibility. Even one star system with the right chemistry could be enough. Life as we understand it depends on a mix of elements. Carbon for complex molecules, oxygen for water and respiration, nitrogen and phosphorus for biochemistry, and iron and magnesium for planetary cores and biological functions. In the Milky Way, these elements are the result of billions of years of stellar recycling. Massive stars explode, scattering heavy elements across space. These later seed new generations of stars and planets. The dwarfs, however, struggle with this process. Their small gravity wells mean that when a supernova erupts, much of the material is blown away. It is blown into intergalactic space rather than retained. As a result, many dwarfs are chemically primitive. They remain locked in a kind of early cosmic state. Their stars contain only traces of the heavier elements. This poses a clear problem for habitability. Planets are harder to form without heavier elements. This is since rocky material comes from those very ingredients. Gas giants would still arise, but stable rocky worlds with atmospheres and oceans may be rare. The smallest dwarfs could be nearly devoid of rocky planets altogether. And yet some intermediate-sized dwarfs show evidence of ongoing chemical enrichment. Within them, astronomers have found planetary nebulae clusters and even stars with more metallicity, more substantial metallicity. This suggests that at least in the larger dwarfs, the ingredients for rocky planets exist. Dwarfs often lack the thick layers of gas and dust that shield larger galaxies, shield them from bursts of energy. Their stars are more exposed to intergalactic cosmic rays and to the fierce winds of their own stellar populations. In particular, many dwarfs contain high numbers of massive short-lived stars. These stars can flood their environments with ultraviolet radiation. This can strip the atmospheres from nearby planets. A world orbiting within such a neighborhood might struggle to maintain liquid water or a protective atmosphere. Life would be pushed underground, underwater, or into rare, sheltered environments. Still, one must not dismiss the protective niches that could exist. Not every part of a dwarf galaxy is equally hostile. Just as deserts on Earth do not prevent life from thriving in caves, oases, or shaded regions, dwarf galaxies might still harbor pockets of stability. A low-mass star, such as a red dwarf, could provide a long-lasting and steady source of energy. If such a star hosted planets, even in a chemically limited galaxy, the conditions for life might still emerge. Red dwarfs are common throughout the universe, and their extended lifetimes, stretching into the trillions of years, could allow biological processes time far longer to develop than around stars like the Sun. Many dwarf galaxies are satellites orbiting through regions where they are bombarded by tidal forces and stripped of gas. This stripping reduces the ability to form new stars and planets, but it also stabilizes their environments over long periods. Once a dwarf loses its gas and stops birthing massive disruptive stars, its remaining stellar population can quietly burn for billions of years. In such a frozen, quiescent state, the small stars and their planetary systems might enjoy long epochs of calm. The galaxy itself may look dead, but on a planetary scale, life could have more than enough time to take root. The ultra-faint dwarfs preserve chemical records from the first billion years of the universe. If rocky planets managed to form in such galaxies, they would be ancient beyond imagination, older than the Earth by billions of years. Life in such places could be unimaginably old. It raises the possibility that the first stirrings of biology in the cosmos did not happen here, not in the large spirals like our own, but in these forgotten corners of the universe. On the flip side, the fragility of the dwarfs might make them extremely vulnerable to catastrophic events. A single gamma ray burst, a supernova cluster, or even a collision with another dwarf could sterilize much of their limited star systems. Unlike the Milky Way, which can absorb such blasts without a significant impact, a dwarf could see entire regions rendered lifeless in one go. The margin for survival is much thinner. Eventually, many dwarf galaxies may be shredded, their stars scattered into stellar halos, their gas absorbed into new star-forming regions. For life within such galaxies, this might mean the eventual destruction of any stable orbits. However, once the stars are stripped and join the halo of a larger galaxy, they may still carry their planets with them. Thus, the remnants of life-friendly conditions in a dwarf could persist, not within the dwarf itself, but within its captured debris inside a larger galactic system. The classic habitable galaxy model suggests that life requires size, stability, and enrichment, heavy element enrichment, all of which favor the giants. But the cosmos is more creative than our neat categories. Even within the harshest dwarf, a single star system might hold a stable planet. A planet with oceans, atmospheres, and biology. The chances are smaller, the risks are higher, and the environments are stranger. Yet, if life is common, then it should appear in every kind of galaxy, not just the grand spirals. This makes dwarf galaxies fascinating test beds for astrobiology. They show us the extremes of galactic conditions. If life can exist there, it may truly exist everywhere. If they turn out to be barren, their emptiness will highlight the importance of galactic size and the importance of chemistry in shaping life's cosmic stage.